Okay, so I'll start my series of lectures. So this is about so-called trace functions of a finite field. And so this will cover a lot of ground, but most of it is joint work with especially Etienne Fouvry and Philippe Michel. And there are pieces which are joint works also with Satadal Ganguly and Guillaume Ricotta, and ongoing joint work with Paul Nelson and Florent Jouve and Will Sawin. And some stuff is in the Polymath 8 project, so a whole bunch of people. So what I'm going to try and describe is, to some extent, a little bit a piece of applied mathematics. So the mathematics we apply is the theory developed essentially around here, between 50 and 30 years ago by Grothendieck, especially Deligne and Katz, Lomont, and a few others, culminating with the Riemann hypothesis over finite fields due to Deligne. And the applications, so what we are interested in are applications to analytic number theory. Or to number theory more generally, but most applications that I'm going to discuss are really in analytic number theory. And what I'm trying to do during these lectures will be to present this part, hopefully for the largest possible audience, so that you can also apply it to your own problems in an efficient way. So the idea is that we're going to look especially at the Riemann hypothesis of finite fields, and at first begin by seeing it as a black box, and then fairly naturally we'll see that, so this black box, to apply it, to use it efficiently, one needs to know a little bit of what's inside. And over the course of the 4 lectures, the goal will be to introduce more and more of what's inside the black box, so that the applications become more and more refined. And in the end, what turns out to be the case is that one reaches quickly, or not so quickly, but one reaches points at where you cannot just take, let's say, especially the works of Katz, and apply them immediately. We reach open questions, very interesting open questions, even from the point of view of algebraic geometry, where hopefully insights from analytic number theory are useful. So this will come towards the end. But today I'm going to begin by trying to present a version of the Riemann hypothesis of finite fields in an extremely general version, but as hopefully a very applicable one as a black box. And we'll learn a bit of what's inside the black box to be able to apply it from this point of view. So as a first kind of reference for what I'm describing, so there's a trace function survey from PISA. So the PISA trace function survey that Philippe and Fouvry and I wrote, which is available on my webpage, for instance. Okay, so the main objects will be these trace functions. So we'll be interested in a prime number P. And so I say prime over finite fields. Really, what I'm going to describe certainly applies to any finite field, but because our applications are mostly over Q, the finite fields will be just, for the most part, just prime fields. So Fp, Z not Pz, the prime field. And we are looking at certain functions. So trace functions will be certain functions, complex valued functions defined on Fp, which have very algebraic flavors. So trace functions algebraic structure. And the actual precise definition is quite involved, so I think that by the end I should be able to give a full definition, but I want to try and show that it's possible to begin a little bit like when you study automorphic forms at the beginning. First time I saw, at least myself, the Peterson formula. Well, there was a Bessel function. I certainly didn't know anything about Bessel functions, but I just started. I knew in such and such a place, I found some bounds, then I found some identities in Greifstein-Ritschig, and you can build a lot just by knowing that. At some point, you want to know a bit better what is a Bessel function, but certainly you don't need to start by studying differential equations abstractly to study automorphic forms using the Peterson formula. So I'm going to take a little bit this special functions approach at the beginning. I'm going to give examples, and at some point, we'll see that we need to know a bit more of where these functions come from. Otherwise, we're kind of stuck when applying the Riemann hypothesis. And then I'll open the box further and further to, at the end, hopefully there'll be a full, strict, rigorous definition of trace functions. OK, so what are the examples? The basic examples. So the first examples one sees are additive and multiplicative characters. So first, just additive characters. EP of n, so EP will be exponential 2i pi n over p. Chi is a multiplicative character of Fp. So these are the more elementary ones that come in, but then in analytic number theory, very quickly you reach things where you replace the argument by a polynomial or a rational function. So in both of these, I think that f is f1 over f2. f1 and f2 are, let's say, polynomials with integer coefficients. f2 is non-zero, and they are coprime. And f2 is non-zero mod p. So we can divide, at least for most n, we can compute f2 of n and compute f of n modulo p and compute the inverse and so on. So these are the simplest examples, and then one very quickly learns that it's useful to be able to mix them, taking multiplicative characters times an exponential. And these objects in analytic number theory, they don't arise usually just like that. We define this function and we want to say something about it. They come out in a natural way, and what one is interested in very often, maybe most often, is not so much one value, but average values. So sums of these things, meaning exponential sums. So these come usually in applications. In the form of sums. Like sums, the first one maybe that one encounters is following Gauss, something like EP of n squared, n ranges over Fp. This is a quadratic Gauss sum. Quite quickly also called Gauss sums are Gauss sums attached to characters. So as long as one is interested just in upper bounds for this, so it might be that you want something more refined. So for quadratic Gauss sums, the most important application doesn't just want the size, it wants the sign, the argument of the Gauss sum. but in many applications, it's really the upper bounds. And as long as you just have these two and you only want upper bounds, you're in very good shape. These are one of the few cases where the modulus of the sum is known. So here, everything is nice. Meaning if I call the first one S1 and the second one S2, then S1 and S2 have modulus coat of P, and S2, this is when K is non-trivial. Okay. And then you might want to tweak these things. Sometimes you see that extra parameters come in, A in Fp, and this would then still be true for A non-zero. So, but basically also one quickly realizes that these are essentially almost the only ones where you can actually compute the modulus exactly. So I guess maybe an even more trivial case is just the full complete sum of just a character over a group, in which case when the character is non-trivial, it's 0. So almost any other sum does not give simple formula either for the sum or for the modulus. When you take as summand one of these special functions I already wrote down, so I guess maybe the other nice exception are Jacobi sums. Salier sums even do have a certain formula, but it's not actually such a nice simple formula. And here the kind of basic case is the Klustermann sum. So classical Klustermann sum in one variable, which I will denote by KL2. So I think this was the notation implicitly used by Tao also, which for us it is convenient to normalize by square root of P immediately. And then this is something which sums over invertible elements mod P and EP of nx plus inverse of x computed modulo P, often denoted x bar. Okay, so Klustermann sums were introduced somewhat implicitly by Poincaré when computing the Fourier expansion of Poincaré series, and explicitly and studied already quite deeply by Klostermann to study representations of integers by quaternary quadratic forms, integral quadratic forms. And for these, so they have many, many, many applications in analytic number theory, and there is no explicit simple formula to tell you what this is or what the modulus is. You need just estimates. So here, one can only hope, and it's a generic situation. Now, one of the important features of this example, which already throws you way beyond the theory of André Weil. So the best estimates for Klustermann sums, individual Klustermann sums, are due to André Weil. But now if you start thinking of this as a function of n, so an important feature is that these sums themselves, as functions of n, are kind of nice. And so it's important to define it also at 0, which I will do by sending it to minus 1 over square root of P. That's the right definition. Actually, that's the definition that comes in there. Naturally, I don't actually have to say anything. So is also such a special function. Modulo prime. And more generally, many families of exponential sum parameterized by some element in Fp will themselves be nice functions in this sense, which immediately will give us a lot more applications of the Riemann hypothesis than just playing around with the first example. So from the point of view of more classical things, you should think of this like KL2s are analogs of Bessel functions in a, in fact, relatively precise sense. And so saying that we want to see these as nice functions is like saying that Bessel functions are just as nice as the exponential function, essentially, or like power functions. So in classical analysis, the first interesting functions are exponential functions and power functions. And when you start going to Bessel functions, these are just as nice once you start learning about them and so on. And this step of going from characters to Clue-Summon sums or such exponential sums is also of this kind. Okay. So the crucial feature that the Riemann hypothesis tells you is that if you look at these trace functions, so whatever they are, we already have a few examples, I will give some more in a second, provided you restrict to a certain subset which are defined by some kind of irreducibility or normalization condition, then they behave like quasi-orthogonal vectors in a finite-dimensional Hilbert space. And this quasi-orthogonality gives you square root cancellation in a generality which is way, way beyond what the theory of André-Weil can give you for just one variable character sums. Okay, so the RH will be a statement such functions. Okay. So now I have to here say a little bit on where the functions come in, but then this almost a definition, but not quite a definition, will be replaced by, again, a series of examples and then the statement of the Riemann hypothesis. So roughly speaking, what happens is that you have certain algebraic geometric data which can be defined in different ways. So it could be Galois representations of the rational function field in one variable, which is, well, it's not quite the same, but you could also think of this as automorphic forms for this field, but automorphic forms of arbitrary rank, not just classical GL2 things. Or you can think of this, so the geometric point of view is something called L-adic sheaves of a certain type. And it doesn't really matter whether you understand any of these words for most of this lecture. So we'll see that there are questions at some point that you can only answer if you really have an idea of what one of these means. The most convenient, I find, is the L-adic sheaf point of view. But the easiest to define would be the Galois representation. So that's probably what will emerge as a definition as time passes. Now, these are algebraic geometric data, and you can think of them really as analogs of automorphic forms. So you know an automorphic form over a number field is a relatively complicated object, but with many nice properties. Or a Galois representation is a nice object, which is highly algebraic, highly structured with many invariants. And we will send these to the space of functions, let me call it C of Fp, which is the space of functions K defined on Fp with values in C. So we have some highly complicated objects. With proper normalization, these typically define countable infinite sets. And we send these to this finite dimensional vector space of dimension P over the complex numbers. So the trace function is an invariant which, again, if you think of analogies with automorphic forms or even with Dirichlet characters, modulo a large modulus Q, you should think of this maybe as being the data of the first values of the character or the first Fourier coefficients of a modular form. So it's not full information about the modular form. If you think of the classical case of GL2 forms, you just take, let's say, the first q to the 10 Ecker eigenvalues or something like this, or q to the 1/2 Ecker eigenvalues. But this is enough to get a good handle on the algebraic object, as we'll see. Okay. So there's one very important fact that is analytically completely crucial. So from the point of view that we have some complicated algebraic object, and then we just take this invariant, which is the trace function. The trace function only a priori contains some of the information, and the map is not injective. So in particular, there are literally infinitely many objects which have the trace function identically 0 modulo p. So if you just think of the trace function by itself as a function defined modulo p, it doesn't tell you that much because it comes from infinitely many sheaves or representations. And some of these are highly complicated, and some are a little bit less complicated. So we need a way of measuring the complexity of a trace function so that we can work with objects with small complexity as a way of saying that we have a control on the function we get and that the function gives information. So it's like saying that if you just look at the value at 2 of a Dirichlet character, it's not telling you that much. But if you know that the conductor of the character is extremely small, then it's giving you a little piece of information. So there is an invariant which is an analog, quite close analog of the analytic conductor for L functions of, so either of these objects, so a sheaf, representation, automorphic form, and we will usually work as p varies with, so for every prime p you would have a trace function kp, which as p varies, so they vary really with p, but they come from sheaves or whatever which have complexity bounded uniformly in terms of p, from objects with uniformly bounded complexity. Okay, and so by abuse of notation, I will write C of k for, so maybe the smallest complexity of an object which gives rise to a trace function k. Okay, so let me say that I will fix, so these objects, you don't necessarily need to know whatever they are at the moment. Let me call them representations. Let me call them rho, and T rho will be the trace function, and assume that trace function is k. And I will use C of rho for the complexity of a representation. Okay, and as you will see, just like you can say a lot about Bessel functions, or you can use Bessel functions quite efficiently just by knowing that they occur in certain formulas and satisfy certain bounds at infinity and certain integral identities. One can say quite a lot about trace functions. One can apply them quite successfully, just knowing many examples, bounds on their complexity, and the Riemann hypothesis, which will come in a second. So first, more examples with examples of the complexities. Okay, and so whatever I'm going to say later, if it seems abstract, you can always go back to these examples. And usually, even with just these examples and a few basic operations, you already have lots of the interesting features, phenomena, and what you need for many applications. So the abstract theory is useful, but it's not necessary to already say quite a lot. Okay, so first there are the examples I already gave. except that I have to tell you something about the complexity of these objects. So we take a rational function, as before. So now I'm going to take the polynomials in Fp of x, coprime, F2 non-zero. And so in the theory, because we are looking at objects which are a little bit like primitive Dirichlet characters, in contrast with just all characters. So the primitivity means we have to be very careful with the value at all, so which would be the prime numbers or integers in the classical case. So we cannot just say that, let's say, at the points of indeterminacy, we don't say what happens. So where F2 has a pole, or F2 has a 0, so F has a pole, we have to say precisely what is the right value of the function. This is important for some statements to actually work. So precisely, so we define K of n to be EP of F of n when F2 of n is non-zero, not P. So in this case, F1 of n is non-zero because the two polynomials are coprime, so the thing makes sense, and 0 otherwise. And for multiplicative characters, we can take chi of f of n if f2 of n is non-zero and f1 of n is non-zero. Okay, so for multiplicative characters, a priori, you also have to say what happens when we evaluate a multiplicative character at 0. And there are two further cases. So if chi is non-zero, if chi is not the trivial character, and f1 of n is 0, or f2 of n is 0, we take 0. So the classical extension of a Dirichlet character at 0 is chi of 0 is 0 if chi is non-trivial, but if chi is trivial, it should be 1. So it's 1 if chi is equal to 1, and f1 of n or f2 of n is 0. Okay, so to a certain extent, this is technical. So in analytic number theory, if you happen to have a different convention for 0, you would just switch the value at this point and do trivial estimates for after the switching. But for the algebraic statement, it's crucial to have the right conventions and normalizations. So that's one. So we have to say what is the complexity. In both cases, the complexity is bounded. I mean, I didn't define it, but I can tell you this is going to be bounded by the maximum or the sum, let's say, of the degree of F1 and the degree of F2 with an absolute implied constant. So one can actually be more precise when one has a correct definition of the complexity, but for basic applications, you just need to know. So how is this useful? It's going to be useful by saying you take f to be a ratio of integral coefficient polynomials, which are fixed. And then you take p to be a variable prime going to infinity. And if f1 and f2 are fixed, the conductor of whatever you have as a trace function modulo p will be bounded independently of p. That's the crucial aspect. Okay, so that's the first example. Second examples are hyperclusterman sums. So let's pick an integer r at least 2, and KLR of n and p is, okay, so here I have to be careful. So 1 over p to the r over 2, r minus 1, sorry. Sum over x1 up to xn in fp. xr, thank you. Such that the product is equal to n of ep of the sum. xr, sorry. And that's when n is non-zero. And when n is equal to 0, again, one has to be careful. And if I remember things right, it's minus 1 to the r divided by p to the r. Minus 1. Philippe, do you remember? I think it's that. Okay. Anyway, so it's important that it's there when n is equal to 0. So there's a way of computing these values, right?
So it doesn't agree with ours.
What?
It doesn't agree with ours.
So r equals 2, I had written 1 over p. Yeah, so is it r minus 1 over 2? Oh, I always forget this one, so. Okay, I'll write this for the moment so that it coincides with the case r equals 2, and I'll correct that the next lecture, because this is something I always forget. Okay, so for I is equal to 3, these are the 3 variable Klustermann sums, or 2 variable Klustermann sums that Tao spoke about when explaining how one handles the so-called type 3 sums in Zhong's work, or the ternary divisor function in arithmetic progressions following Friedlander and Iwaniec. No, you can write it this way. So if n is 0, I mean, if n is a multiple of p, that means n equals 0, then you have to use the second formula anyway. And if n is non-zero, then the xi have to be invertible. Yeah, or everything is defined over fp. All my functions will be defined just over fp.
Okay, so you could actually write fp star then on top.
Yeah. But I mean, I always forget how you. So I mean, Deligne defined is the first, and if you write it correctly, then the n equals 0 case is given by the same formula. I'm not sure if the way I wrote it down will actually give the right formula for n equals 0.
I think it should be r minus 1.
The exponent?
1 to the power r minus 1.
Well, yes and no, because I mean, for I is equal to 2, I switch the sign. I mean, the right definition of Klustermann sum is minus 1 over square root of p times the sum for I equal to 2, which I didn't do, so I just. Anyway, so it's not an important thing. I'll clarify this the next time. But for I equal to 2, you should have. Yeah, you're right. It's probably r minus 1. Anyway. Okay, so this is a deep fact. Is that these are trace functions. And this is due to Deligne. And I can show you that this is indeed a deep fact by the following first another fact about the complexity. So I didn't tell you about the complexity too much, but there are 2 properties of the complexity which are. Maybe I should say this after the next example, but I might forget. So let me say it now. So it's a little bit, this is kind of semi-digression, but it comes at a good point because the strengths of these remarks will be clear. So 2 facts about the complexity are important. So the first, it's a little bit like a height, in the sense that when you look at the set of trace functions with a suitable normalization, which I will discuss later, with complexity bounded by a constant, this is a finite set. So the whole set of trace functions is infinite, just like the set of Dirichlet characters is infinite. But when you bound the conductor of Dirichlet character, you get a finite set, and this is a similar feature. So this is a rough way of saying it, because we need a little bit more information before we can state this precisely. But roughly speaking, the set of K with complexity less than or equal to x is finite up to trivial modifications of the trace functions. So this is a relatively rough statement, but it gives an idea already of what is the content. And so, as you maybe know, is if you take the analytic conductor as defined by Iwaniec and Cernak, the same statement is true for automorphic forms over a number field. Okay, and the second remark is explanation of why this is really deep. A basic fact about the complexity. So one has already a first way of showing that the complexity is interesting. The way it's defined, it has the property that the L infinity norm of K is bounded by the complexity. So whatever complexity you have, it should measure how complicated is a function. One way that a function can be complicated is by taking large or very oscillating values. And here we're saying that the L infinity norm is bounded by complexity. And here, what I didn't say, which I should have said, sorry. So with the complexity of KLR, mod P is bounded by 1 with a constant depending only on R. So let's apply this fact. So Cluster sums are trace functions with bounded complexity, and the fact that the L infinity norm is bounded by the complexity, whatever it is. So corollary immediately is that there exist constants AR non-negative such that the hyperclusterman sum NP is bounded by AR for all n mod P and all primes P. Now, because I divided by, let's say for R equal to, I divided by square root of P, this is a weak form of the Veil bound for Clusterman sums. So if A2 was equal to 2, then this would be the Veil bound for Clusterman sums, which comes directly from knowing that it's a trace function with this type of properties. And so it's not surprising then to see that to prove this, that these are trace functions in the sense I'm mentioning, so Deligne used already the Riemann hypothesis of finite fields in a non-trivial way.
How complicated is the zero function?
Bounded complexity. I mean, it depends the way you define it, but I think with our precise definition it would be 1.
Oh, no, okay. I thought you were saying like it's possible to have a trace function which is identically 0.
Yeah, with large complexity. So, but the smallest complexity will be 1. And actually, it's an interesting question to find the smallest complexity of a non-zero function with non-zero object with trace function 0. And this I actually don't know. So the lower bounds, I mean, the upper bounds we know is P, or lower bounds. So we know trace functions with complexity roughly P, which have, sorry, we know objects, representations, with complexity roughly P with trace function 0. And what is the actual threshold, I don't know. Okay. Good. So already this is, you see that just knowing that an object like hyperclusterman sum is a trace function without knowing anything else, so this is a type of information that maybe in 10 years there'll be an analog of Grafstein-Rijik for trace functions, and this is the type of thing you would find in the first 2 pages of this hypothetical motivic Grafstein-Rijik, and you wouldn't need to know anything about Veil bound or hyperclusterman sum bound. You would just say this is a trace function, so it's bounded by complexity. Complexity is bounded, and then you apply that. Okay. So this is somewhat similar to the fact that Bessel functions decay like 1 over square root of x at infinity. I mean, in a very rough analogy. It's a much deeper fact, but okay. So now let me go back to, after this small digression, to more examples to show you the variety of type of things that can arise. So another fairly general class of trace functions are those which you obtain by counting solutions of certain polynomial equations. So first example would be you fix a non-constant polynomial f mod p. It could be a rational function also, but I do it for a polynomial, and you count for a given n how many x there are in fp with f of x is equal to n, and you just count them. So this is integral valued. It's only bounded by the degree of f because f is not constant. It could be 0 and it will be 0 fairly frequently, but it is something. So this is a trace function, and its complexity is bounded in terms only of the degree of f. Oops. Oh well. So then, so K is a trace function with C of K, again up to an absolute constant bounded by the degree of f. And therefore, if your polynomial is, let's say, x squared, which is an integral polynomial, then you get something which has complexity bounded independently of p. And in this case, of course, it's not hard to compute. The number of solutions to x squared is equal to n. It's 1 plus n over p. And the last example, which is, again, just a very special case of something more general, is if you try and count not the solutions to this type of one-variable polynomial equation, but number of points on the family of curves. And the simplest example is, really interesting example is probably the Legendre family of elliptic curves. So you take k of n to be p minus, in this case, one has to normalize it in this way. So the number of solutions in fp squared of y squared equals x minus 1, x minus n. So this is done in such a way that the formula is correct also for n equal 1 or 0. So that works for every n. So is a trace function. I have to divide by square root of p with my definition. So it's the AP of this elliptic curve divided by square root of p. So it's a trace function with complexity bounded as p varies. And you can basically replace this family of elliptic curves by almost any family of algebraic variety, depending on one parameter that you can think of up to technical issues.
Wait, by technical issues, you mean what exactly?
And your dimension.
Well, I mean, you might have to extract the right.
At the bad point.
Well, first there's the bad points, and also if let's say if you take a surface and if it has, let's say, an H3 instead of, this would only be the right thing if there's just a middle dimensional cohomology or whatever. But for families of curves, this would, except for doing the right thing at the bad points, this would be the right. This would almost always be a trace function. Okay. So this already gives you some insight. And so one of the things you can see is that once you have this, already just with these examples, any statement which is valid for any trace function, which there will be such statements, will immediately give you many, many different types of statements, which very often analytic number theory would otherwise be kind of treated one by one with maybe different ad hoc methods. And we'll see examples of some of the things we did with Fouvry and Michel, where we have statements which are valid for every trace function. So that looks a bit abstract at first. But once you have a list of examples, then you see we have actually lots and lots of theorems. OK, now I can state the Riemann hypothesis. Right, I guess I need a bit more room for such a big theorem. So I think I'll keep the examples visible, at least their definition, if I do it this way. So, because you will see that I'm going to state the Riemann hypothesis. I cannot quite state it just with using only the words I've already introduced. I will need to introduce at least one extra property of trace functions, which I will then interpret in a concrete way to see that this statement at least implies almost immediately the qualitative version of Veil's estimates for exponential sums in one variable. So I keep this definition because I want to be able to refer to them. So because the extra word I'm going to introduce will be a conditional trace function, it will be always satisfied for the example one, which is the classical exponential sums in one variable case. Okay, so theorem. So this is essentially the lean, but it uses also work of Grothendieck and a few other people, but these are the two main ones. And the really essential work is that of the lean. Okay, so P is a prime. And we take K1 and K2 trace functions modulo P. with complexities at most C1 and C2 respectively. So I could say equal to C1 equal to C2. I want to emphasize that usually complexity, you don't really know what it is because it's not such a very meaningful number. What is meaningful is being big or being small. So, and you have to think, let's say, of C2 equals 10,000, C1 equals 10,000, and there's already lots and lots of such things, as the examples above already show. Okay, now we need an assumption on K1 and K2. So the statement will be a quasi-orthogonality statement, but for that we will need some assumption. So we assume K1 and K2 are what is called geometrically reducible. So I will have to explain what it is, and I will do it afterwards. You can already take as information that in case 1, this is always true. So in case 1, if you have K1 and K2 both of this type, so one additive, one multiplicative, or both multiplicative, both additive, whichever way, then it is always automatic. Then there are two cases. So if ρ1, okay, so, and they are associated to representations, let's call them whatever these underlying objects, which I call ρ1 and ρ2. So if ρ1 and ρ2 are not geometrically isomorphic, so it's another piece of information I will have to explain, and I will do it afterwards. And in case 1, in the case of one variable character sums, it will again be quite clear what this means. Then we have square root cancellation when we correlate K1 with K2. So we sum over FP K1 times K2 bar. So it's an inner product. And we get square root cancellation with implied constant depending only on the complexities. And one can compute that the upper bound can be 3 C1 squared, C2 squared, with the definition we've taken of complexity. Okay? So this is uniform square root cancellation as long as you have the assumption and as long as C1 and C2 are bounded. I mean, it's even uniform in such a strong way that you don't need to have C1 and C2 bounded. They could grow a little bit with P, and still you get extremely good bound. So that's the first statement. Let me put the second part here so I still have the examples on the blackboard.
Is this condition independent of the row 1 and row 2 are sort of not unique?
Right, but that's the condition to have this is that row 1 and row 2 are. It's a condition about row 1 and row 2. So what this will reveal is that once we have the second version, what this will reveal is that there can only be one row 1 with small complexity and with a given trace function. So there's a gap between the complexities of the trace function. That's a little bit what actually I was asking. Okay, so second statement is what happens in the other case. So if row 1 is geometrically isomorphic to row 2. Okay, so first thing is we don't know what that means, but first a consequence which we might be able to falsify, meaning that if we falsify this condition, then of course we're in case 1. So then first information is that K1 is proportional to K2 for some alpha with modulus 1. It's really proportional everywhere. So including possible bad points. That has to do with the fact that we're using implicitly correct definitions of the values at every point. And then it's not orthogonal, but quasi-normed, meaning that the sum of K1 of x, K2 of x, conjugate. Well, of course, it's alpha times the sum of modulus of K1 of x squared, so we cannot expect cancellation. And in fact, what we have is more like an asymptotic formula. This is alpha times p. So in particular, if K1 is K2, this is exactly p. And up to an error, which is again square root cancellation. And the same bound as in the case here. Okay. So I have Still about 10 minutes. Okay, so once we understand a bit better what these conditions mean, and we have tools to handle these conditions, checking them and so on, then this is really an extremely general black box version of the most general form of the Riemann hypothesis of finite fields. So it's not quite equivalent because we're still working with just prime fields and sums with one variable, but it's basically the whole thing. At least from the antinomosy point of view. I mean, there are other consequences of Delin's work, which are more algebraic geometric, which this is not really trying to catch. Okay, so now, yeah.
If you take the product of two trace functions,
Yeah.
I guess maybe it's not quite a trace function because of that.
Right. Yeah, exactly like products of two Dirichlet characters, which are primitive, might be primitive. You might have to change at the bad points the value to get something primitive. But there's a unique underlying kind of primitive object that arises from this.
Emmanuel,
Yeah.
is twice a character also a trace function?
Yes. But then it's not geometrically reducible. It would be chi plus chi, two different components. You're only allowed to multiply, if you multiply chi by a complex number of modulus 1, you can say that it's still a trace function that's geometrically reducible. But if you multiply by 2, I mean, there are different ways of doing it, but the allowed way is to do chi, direct sum with chi, and then the trace. And this is not irreducible anymore. Yeah, because otherwise it wouldn't work.
How about the K1 equals K2 here? How about the K1 be equal to K2?
So K1 equal to K2, you're in this case, and then
You say the rho 1 geometrical is small equal to rho 2, then K1
Yeah.
equal to alpha K2. But how about the K1 not equal to alpha K2?
if they are geometrically reducible, then this is true. And otherwise, this is going to happen in situations where the complexity is so large.
Not equal.
Yeah, it certainly can happen that they are not geometrically reduced, they are not geometrically isomorphic, but K1 is equal to K2. This can happen, but then the C1 or C2 will be extremely large, so that this bound will be trivial. So you see, this bound is very powerful when C1 and C2 are small enough that essentially the product is less than square root of P. Because what is the trivial bound? Maybe I should have said that, but so the trivial bound for these sums, K1 of x, K2 conjugate of x. So trivial bound is P times the L infinity norm on both, and we know this is at most C1, C2. So you see that if you allow complexities too large, then this is a meaningless, gives no information. So there's no contradiction. Okay, so what does it mean to be geometrically reducible? So geometric irreducibility and isomorphism. Yeah.
In the second statement, we write that C1 equals C2.
Yes, right. Yeah, that's so the invariant is an invariant of. So these objects 1 and rho 2, they're really meaningful up to certain isomorphism class, and in particular, C1 equals C2 in that case. Okay, so what does this condition mean? So here we have to enter a little bit into where these functions come in. So if K is a trace function of a certain object rho, this implies there exists a homomorphism. So rho is really a homomorphism of a certain group pi 1, to a certain finite dimensional vector space. So it's a finite dimensional representation. You can think of V as a complex vector space. This is algebraically not the right thing to do. It should be an L-adic vector space, but it's only fine algebraically to think of it as a complex vector space of some finite dimension, such that K of n is the trace of rho of certain elements, Frobenius elements depending on n, acting on a certain subspace Vn of V. So Vn is the invariance under inertia, which I don't want to go into right now, but the subspace of V. Okay? So at first you can even ignore this second information. So there is certain object. So rho is really a map from a certain fixed group. So this is depends only on P into a finite dimensional vector space. So GL of a finite dimensional vector space. So if you have a representation, you can ask that the representation is irreducible, and this is almost what we want. So precisely, there exists a normal subgroup pi1g of pi1, and to say that rho is geometrically irreducible will mean that there is no, this does not exist, so means first V is non-zero, and there does not exist W inside V, not equal to V, non-zero, stable under the action of the subgroup. Okay, I'm still trying to keep all my examples, but it's becoming difficult. What?
Is this for every normal subgroup? Is there one?
No, there exists such a normal subgroup. So, okay, more precisely. So I can tell you what is pi1 then, if, so that there's no ambiguity. So pi1 is just the Galois group of a separable closure of Fp of t. So it's a group that depends only on P, up to isomorphism, and the normal subgroup is the Galois group of the same big field. So algebraic closure of this function field modulo the smaller group of rational functions with algebraic coefficients. So it's not, I mean, in some sense, these are not such complicated objects. They are quite mysterious from the group theoretic point of view, and often one doesn't need to know really what they are, but that's what it is. Okay, so we have this condition, and therefore, in particular, so suppose that the dimension of V is 1. So this happens in case 1, in the first example. So meaning character values at a rational function, additive or multiplicative. So one has to know that this is the case, but this is the case. Then in this definition, you don't need to know anything. V is of dimension 1. You're looking for, so it's non-zero. You're looking for a proper subspace that's non-zero. There are no such things. So it is automatically geometrically reducible. So that's an example. Okay. Next, geometrically isomorphic. So ρ1 into GLV1 and ρ2 into GLV2 are geometrically isomorphic if and only if there exists a linear map isomorphism, linear isomorphism from V1 to V2. So they are the same dimension. There's a linear map such that, okay, I have to write this diagram correctly. So for every element in the group, whatever this group is, this diagram commutes. It just means the action for every G in the subgroup. So gamma, I should call it pi1G. I mean, as a first instance to begin with, what you should think of at the moment as what does it mean to be geometrically isomorphic means trace functions are the same. That's what you should think of, and we'll see more refined versions of this in a second. Okay, now it's becoming harder and harder to. Okay, I'm starting to get a bit over time, but since I'm an organizer, I'm allowed. That's not the right one. So I want to show how this immediately tells you a qualitative form of Weyl estimates. So just by knowing this, you already can apply it well enough to recover Weyl's estimates for one variable character sums. Okay, I guess I have to erase that. Okay, so example. And I'll just do the Klusterman sum case for simplicity. That's the most interesting one for many applications. So R equal 2. So in that case, you take K1 of x to be the Klusterman sum. Sorry, you don't take Klusterman sum. You take EP of nx plus x inverse with the usual convention that it's 0 when x is 0. When sorry. There's no n. Going too fast. So you have a non-zero element which is fixed. Let's call it A to avoid confusion. And K1 of x is EP of AX plus x inverse for x non-zero, and is 0 for x equals 0, modulo P. For K2, you take the function 1, which you can see as EP of 0 if you want. So it is a trace function. And by example 1, and by what I just said, so complexity of K1 is bounded independently of P, and complexity of K2 also. And they are certainly geometrically reducible because of rank 1, as I said. And therefore, now I have to erase that. Start with these examples again tomorrow. So we deduce from RH, in the form I stated, that the Klusterman sum with parameter A Fp is of modulus bounded by square root of P with an absolute implied constant. Provided these two things are not geometrically isomorphic. So whatever rho 1 and rho 2 are not isomorphic geometrically. So can it be that they are geometrically isomorphic? Suppose they are, then what happens? That means in particular by case 2, so if they were geometrically isomorphic, K1 would be proportional to K2. K2 is a constant, so K1 would be a constant. And as soon as you have one element non-zero, this function cannot be constant. This has modulus 1, this is 0. So the constant would have to be 0, but then it doesn't work. Okay, so as long as you have a field with at least 2 elements, you're fine. Okay, but K1 is not constant because P is at least 2. So we get kind of a qualitative form of Veil's estimate without having to know anything at all except a black box. Okay, so I'll stop here, and tomorrow I'll start to try and do more complicated examples. So I'll try to start doing the sum that comes up in Zhang's work and see where we get stuck and why we need a bit more information. Thank you.
Can we make a more refined version of RH so we could take this inner product of K1 and K2 and say scale that x and K2 by some n and then normalize by 1/√P? Would that also be a trace?
What do you mean?
So I'm trying to generalize the construction of Klusterman sums here. So they're sums of some K1 times K2, where one of them is with a scaled argument.
So by scaled argument, do you mean?
Yeah, the A.
So
I want like the sum of K1x times K2 nx.
right, yeah. So this will be no problem. So we'll see. So trace functions, not only we have these first examples, but they also have a rich formalism. And in particular, if you replace x by n times x for any non-zero element of the field, then you get another trace function with the same complexity. Or you could replace it by 1 over x, works exactly the same.
But now this sum is a function of
No, you vary n.
And then you want this as a function of n, then this will often be a trace function. There has to be conditions, but for kind of standard random examples, this will be a trace function, and the complexity will be bounded solely in terms of complexity of K1, complexity of K2. This is highly non-trivial, so this will require very recent work of Katz on multiplicative convolutions. But this exists, yeah.
In that example where f is x squared and the Kn is 1 plus the Legendre symbol, this doesn't cancel on average.
Yeah, because it's not geometrically reducible. As you can see. So one of the consequences you can already of what I said is that for small complexity, the two estimates I wrote are incompatible. So the fact that there's cancellation if you take K2 equal to 1, if you take K2 equal to K1, if sum of K1 squared, modulus squared is essentially P, this is equivalent to geometric irreducibility for small complexity. So one quick way, I'll say it tomorrow, but one quick way to, if you are given a function, you know it's a trace function, you want to know whether it's geometrically reducible or not. Compute the mean square. If the mean square is close to P, then it is geometrically reducible. And we'll see examples. So finally, you can check that Kloosterman sums are geometrically reducible this way. The mean square of Kloosterman sum is easy to compute. It's essentially P, so just by RH, actually. So I'll say this tomorrow in more detail. Yeah?
So is it, if you are given something that is not irreducible, is there some natural way to break it up into pieces?
Right, so we know there exists a decomposition into sums of geometrically reducible pieces. There's a little technical tweak, but essentially it's true. It might not be easy to find them. So in principle, you find them by taking inner products. It's like a little bit like an orthonormal basis of a Hilbert space, but there are infinitely many basis vectors. So we have a finite dimensional space, but somehow with infinitely many basis vectors. So it's hard to actually compute all of them to determine the decomposition. So if you cannot compute it because you have extra information, it can be very hard. So a number of the open problems we still are fighting with in various applications is because we have something, we don't know that it's geometrically reducible, and we don't know exactly what are the components. So it's one of the fundamental problems that can arise in applications.
Another question? Okay.
Thank you. Okay, so I wrote down again here the main theorem, so the Riemann hypothesis in the way I phrased it yesterday. And here I recall the 4 examples I had written, and I wrote down with the normalization the way I define Kloosterman sums, this is indeed the right value. Okay, so I want to do, as a first step now, is to try and give another example of trying to apply this as really as a pure black box and see where we get into a little bit of difficulties and then introduce further invariants which will solve this difficulties. Before I do this, I want to make one or two more comments on this condition of geometric reducibility, which necessarily comes into this theorem. So first, what happens among the examples? So examples 1 are always geometrically reducible. So this I mentioned yesterday because the underlying vector space has dimension 1, and one-dimensional representation is always irreducible. 2, one can show is geometrically reducible. This follows either from the construction or by the Diophantine criterion, which I will state as the second part of this remark. Example 3 is never geometrically reducible except if f has degree 1. So f here is a polynomial which is non-constant, so at least 1. So 3 is never geometrically reducible if the degree of f is at least 2. Simply because there's always the kind of the average value of this representation number is always 1. And that corresponds to the fact that there is a trivial component which one can take off. And so k of n minus 1, so when it's defined in this way, is also a trace function and is very often geometrically reducible. So if you remember, the simplest example was when the polynomial is x squared, then k of n minus 1 is just the Legendre symbol n mod p, and this is of an example of case 1, so it's geometrically reducible. I should say maybe in that case, the dimension of the underlying v for k is the degree of the polynomial. Okay, and case 4 is like most families, at least, of elliptic curves. It is geometrically reducible. Okay. So that was example. Going through the examples and trying to see which ones are geometrically reducible. So you can try to apply this theorem then to many exponential sums, because just on these examples, you already get many statements, most of which you would not be able to prove directly without applying the Riemann hypothesis. So there's code cancellation. If you take, let's say, a Kloosterman sum times example 4, conjugate, this is not something you can hope to prove directly. Okay, so second remark is, what is the meaning? So there is often a very convenient Diophantine interpretation of geometric irreducibility that can be used at least to guess that things are geometrically reducible. Quite often actually can be used to prove it. So it's also a consequence of the Riemann hypothesis, and it was, I guess, first stated explicitly by Katz, and it states the following. So I'm going to state it formally as a proposition in a way which is convenient for analytic number theory. So there's a more general version which is more convenient for certain more algebraic questions. So assume we have for every prime p a trace function kp with complexity uniformly bounded as p varies. So in analytic number theory, this is often the situation. So for every prime p, there's a different trace function, and the complexity on the other end does not grow with p. Then so one can phrase this as an if and only if. For the application I want to point out, it's more interesting in the direction of proving geometric irreducibility from something. So I'll just take the if component. So if you compute the L2 norm of kp over fp, and if this is equivalent to p when p goes to infinity. So this is something you might hope in a number of cases to compute analytically. And if you have an asymptotic formula that begins with P, so intuitively this means that on average these things are 1, so because they are bounded and the size of the sum is P. Then Kp is geometrically reducible for P large enough. And one can be more precise. But I think this gives a rough indication, and in many analytic applications, this is certainly enough to guess at least that something is geometrically reducible. You might not be able to get the asymptotic formula, but you might have good heuristics to guess that the leading term is P. Yeah?
So you can weaken these to being bigger by P to the 1/2 plus delta.
Yes.
Is there an example where it has been used?
I think
something is said in journal arithmetic, but it's for the...
Yes, that's a good remark. So let me first address the remark and then come to my examples. So what Philippe says is that, so something I have not said, but the underlying proof of this gives more information, and one component of this information is that, so if one can show, so if you can find some exponent delta positive independent of P such that this L2 norm is at least P to the 1/2 plus delta squared, then in fact it will have to be at least of size P. It won't tell you that it's equivalent to P because it could be more than 1, but at least you would get that. Then one gets for free that the sum is at least P. With these conditions. So I'm still working under this assumption that the complexity is bounded. So this follows from the underlying type of results of Deligne, which actually are specialized to state this theorem. And this, I think, so the one case I know where this is used is there's a paper of Bombieri and Bourgain. So a paper on applications to a problem of harmonic analysis, Kahn's ultra-flat polynomials. So it's not really necessary because they first give a proof by Katz of the estimate they need, and then they reprove the same estimate kind of more directly by using the fact that if you get a tiny compensation, then you get at least square root of P. So it's more in the opposite direction, but so here I could actually say, so if you can, this process goes both ways. So if you can bound, well, I guess then it would not be the L2 norm. So let me not try to give the two. So, but the principle of this discrepancy, this fact that the exponents tend to jump between 1/2 and 1 with no gap, is found in this paper of Bourgain. Is used in this paper of Bombieri and Bourgain.
Is there an inequality between the complexity and the dimension of the underlying V?
Yes. So I think I said that yesterday. So the complexity is among other things. So I stated that it's at least the L infinity norm, but in fact, it's also at least the dimension of V. So if I write rho. So by the end of this lecture, we'll have almost all the components of the actual definition of complexity. And then on next week, I will have to introduce the last one, which is necessary to handle certain cases. Okay, so as an application, I think that you can now, so you can certainly now check irreducibility, so geometric irreducibility of examples. Well, one we already said, but if you didn't know that there's an underlying vector space, so the nice thing about this criterion is that in some sense, you don't need to know that there's an underlying vector space. It's just a purely Diophantine statement. You might be able to verify it without knowing anything about any underlying algebra. So you regain case 1 if f is a fixed polynomial or fixed rational function defined over Q, because then the modulus is 1 except at boundedly many points where it's 0. So this is only true. You can check easily case 2. So it's for r equal to 2, the modulus square of Clustermann sum is very easy. Actually, it's a Fourier transform, so it's a Plancherel formula. For r at least 3, it's a slightly more complicated computation, but it's still elementary. So, and you get that it's equivalent to p. For case 3, you can do certain cases at least. So because I didn't state an if and only if, this would not allow you to deduce that it's not geometrically irreducible, but that's not the most interesting application. And for case 4, I guess it would work. Let me say it's an exercise. I didn't verify whether the mean square of the number of points on the Legendre family is actually easy to compute. I would guess that it is. It should be of the same complexity as Clustermann sums. Okay. Okay, so now we have so we have a black box. At least some of the terms in the black box we can interpret very concretely, even if we don't care at all about the algebraic geometry. So geometric irreducibility you can replace to some extent by this criterion. And geometric isomorphism, you can just try and replace it by proportionality of trace functions. So let's try with this to prove an important exponential sum estimate and see whether there are difficulties. So this example comes from the work of Friedlander and Iwaniec. So in studying the ternary divisor function in arithmetic progressions to large moduli, as explained by Terry Tao last week, or early this week, I guess. So they found that in the end, everything could be reduced to a good estimate for the following exponential sums. I will call it Fi. It depends. Well, actually, the way they write it is a bit different. I will write it with 2 parameters A and B. So A is non-zero mod P, and B is anything in Fp. Okay, so it's not actually exactly the way they state it, but that's the way it comes up in the proof. So that's the natural way of writing it. That's the way that Terry wrote it last time. So KL3 of x, so a variable Clustermann sum with 3 variables, or 2 variables. Then multiplicatively shifted one, KL3 of ax p. And then because they have to use completion techniques to sum of shorter intervals, you need an additive character, so EP of bx. Okay, so estimating this sum was the crucial step for them, and they basically need square root cancellation. So the way they actually write it down, or one way to write it down, is as expanding the 2 Clustermann sums. So if one does that, which is not actually the best way to think about it.
Their initial sum was the expanded one, so it was not grouped.
Well, I mean, really? I mean, it seems hard for me to get, but yeah.
Yeah, in their papers they expanded.
Okay. Well, I mean, they expand, but they expand after. They never write it this way. That's true. Yeah. But anyway. So I think so. This is only appearing in the paper of East Brown. So he writes this explicitly. Okay. So if one expands the Clustermann sums, the hyper-Clustermann sums, naively, this is a 5-variable additive character sum. And the bound they need is code cancellation. So if you write it as a 5-variable character sum, and if you just shifted a little tiny bit the coefficients in a random way, then you would get a genuinely irreducibly 5-variable character sums, and basically you would be, in most cases, rather stuck, even now. So at that time, this was a little bit before the ideas behind such very general versions were completely available in the literature. So the proof of the necessary estimate was given by Birch and Bombieri in an appendix to the paper of Friedlander and Iwaniec. So they proved this required code cancellation. So in the cases where it makes sense. So what are the obvious obstructions? So the only completely obvious naive problem that can occur, sorry I forgot the complex conjugate, is when A is equal to 1, then there's a square here, and B is equal to 0. In that case, it's really the modulus square over KL3, and that cannot be, there cannot be cancellation. So if A is different from 1, or B is non-zero, so A equal to 1 is permitted if B is non-zero, then you have a uniform square root cancellation estimate for all P, for all primes and all A and B. So uniform in terms of A and B and P. So why do I say it's a root cancellation? Remember, the KL3s have been normalized by dividing by P, because R is equal to 3. So the fact that these are bounded in L infinity norm already tells you that the KL3 is bounded by P, which is already square root cancellation, actually by P to the 3/2, sorry. So it's already square root cancellation there. It's encoded in the KL3. And so what we want is square root cancellation in this sum of bounded terms. But when you expand everything into a 5-variable sum, this would be, for this 5-variable additive character sum, P to the 5/2. So this is equivalent to P to the 5/2 for the 5-variable sum. So full square root cancellation. And I think, I don't remember exactly how much they can lose about that in the argument, a little tiny bit, but not very much. So you really need, it's only P squared would not work, if only because this would be the trivial bound from this side. So P here, which corresponds to P squared, would be a trivial bound. So let's try and give a proof of this using what we know and see whether there's a problem. Okay, so we want to write this as K1 times K2, so you can define K1 of X, for instance, to be KL3 XP. K2 of X is KL3 AXP, EP of minus BX, so that the conjugate is the second term. So this one is a trace function. So the second one, it's part of a relatively easy part of the formalism, which I will state in more general versions later, that this is also a trace function. It's not very difficult to prove. And in both cases, the complexity is uniformly bounded with P, and with A and with B. Okay, basically, because here we're taking the product of two trace functions, and each of them has bounded complexity as P varies, either by things I already stated or by easy formalism that I will state later. Okay.
How hard is it to get specific numbers for these bounds?
Oh, for the complexity?
Yes.
Oh, it's very easy. But I mean, it's to some extent, so this complexity you have to think of as a naive height. So it would be, if you think of Akshay-Stock, it would be like the more naive versions of the actual R that occurs in the exact formula. So for analytic purposes, for bounds, it's enough to have a rough quantity, but when you want to do really algebraic things, you might want to have a definition that's more precise. But here it doesn't really matter. Okay, so K1 is geometrically reducible. This is fine. We just checked it. And by using the Diophantine criterion, it can really be checked without knowing anything. K2 also, we're just multiplying with something of modulus 1, so it doesn't change the geometry, the Diophantine criterion. And X goes to AX is a bijection on FP, so it also doesn't change anything. So now the question is whether they are geometrically isomorphic or not. So if K1 or the underlying rho 1 and rho 2, K1 and K2 are not geometrically isomorphic, then we are done. then RH gives Birch-Bombieri. Okay, because this estimate, the first part, so the C1 squared, C2 squared is an absolute bounded by an absolute constant, so this is exactly what I said. Now, this can fail. So an obvious case where it's going to fail, if we think of this proportionality criterion, is if A is equal to 1, B equal to 0, then this of course fails. And we want to show these are the only cases. So is that the only case? So in other words, we reduce to a priori simple-looking problem, concrete problem. Does there exist an alpha such that KL3 of x is always, with modulus 1, alpha times EP of minus bx KL3 of AX. So it is not, I mean, it looks very concrete. This is something you can certainly check by computer for small primes that it's unlikely to be true, but it's not so obvious a priori how to prove that. So last time when we proved the kind of Weil bound, qualitative form of Weil bound, we used the fact that the summand of the Klustermann sum was 0 at a point where the other summand, which was constant 1, was not. Here there's no, I mean, the obvious point where things are strange is 0, but it's the same on both sides. You can try and take the modulus. Of course, KL3 of XP should not have the same modulus as KL3 of AXP if A is not 1, but how do you actually prove that? It's not so simple. So it's not entirely clear. So I think you can probably extract some kind of proof by some means, but I want to use this as a pretext to introduce more of the underlying data to see what can be done. Okay. So there are actually different ways of doing this. There's one which starts with a little trick, which I think is also good to see. There's nothing that says that we cannot try to use analytic techniques to study this sum. And if you actually use a little bit of analysis, so you can try and do Fourier transform, apply Plancherel, or you can just expand the Klustermann sums and be a little bit more careful than writing it as a 5-variable sum. And if you do this, you will reduce to a 3-variable character sum by using orthogonality. So expanding KL3s, applying orthogonality and regrouping in some ways. You obtain a different formula, which is actually the way it's written explicitly in the, at least in the appendix of Birch and Bombieri. So they actually write it in this way. So you sum over T. And you have now a 2-variable Klustermann sum at 1 over T and a KL2 at A over T plus B. So I don't put the P, it's implicit. And here you have to think that T is non-zero and not equal to minus B to not have infinity. Or you can simply sum over FP, the same thing, and just use the definition that KL2 at infinity is equal to 0. And actually, this is a reasonable thing to do, as we'll see. So what we have gained here is, so for Birch and Bombieri, this was important because now if you expand, it's a 3-variable character sum. So they actually succeeded in applying Deline's work for higher dimensional sums to estimate it and get code cancellation. You can also use this form to get a quicker approach to this black box version of the Riemann hypothesis. The point being that here, so there's a special point which is t equals 0, but it corresponds to t equals minus b on this side. So you kind of immediately guess that if b is not 0, this will have code cancellation. Okay, so applying RH to, so now we do another change of variable, which is again permitted by the formalism that I recall, which again, because it's just a bijection, at least of the projective line, is always bounded complexity. KL2 of A over T plus B is also bounded. So we see that so K1 tilde, K2 tilde are geometrically reducible, for instance, by the Diophantine criterion. And K1 tilde is not proportional to K2 tilde, at least if B is non-zero. So because the value, so values at t equals 0 do not coincide. So one value at t equals 0 is 0 and the other not. So at least it's not, so this is KL2 of A over B, and so when P varies, there's no reason for KL2 of A over B to always be 0. Actually, if you think about it, it's not obvious. You need to actually prove something. So I should say probably not. So that's the point, is that, I mean, this certainly is very suggestive. But because we don't have as simple cases as like the veil case where everything is of modulus either 1 or 0, it's easy to see that the KL2 should not be always 0 at A over B, but actually proving it might require some argument. So actually proving that Kloosterman sums are non-zero because it's a KL2 you can do by hand. But in more complicated cases, this type of trying to use just proportionality will give you completely O plus type of very concrete looking, very obvious looking question, but not situations where you can do something. So we need a little bit of extra formalism to handle that case. So I will now go into this direction, but I would like to first so I wanted to present another application where just the black box version is enough, but I don't think I will have time, so I'll do that later next week if I have the opportunity. So we need some more formalism. And then we'll come back to this exponential sum estimate. And there will always remain the case where B is 0, but we have to prove that when A is not 1, it's not proportional. That's also not obvious. Okay, so formalism, so we already saw some of it coming naturally in defining even these very special cases. So one was something that was mentioned already. It's the decomposition in geometrically reducible pieces. So to be precise, this does not quite work in the generality I'm going to state. There's a slight technical issue between representations which could be reducible as representations of the group I called pi1, whereas geometric irreducibility is irreducibility as representation of a slightly smaller subgroup. So there could be a discrepancy. It's not hard to deal with, it's just a bit technical. So I'm going to state something that's a little bit false, but in papers you can see the actual version stated correctly. So any k, which is a trace function, can be written as a sum of at most the complexity of k geometrically reducible summands ki with complexity of ki at most the complexity of k. So if I don't put geometrically reducible, this would be literally correct, but geometric irreducibility is what you need to have this form of the Riemann hypothesis. So this is a technical issue which in applications has never actually come up concretely, so it's worth not trying to think about it too much at the moment. So elementary, more elementary things. So if you have representations, if you have two of them, you can build a direct sum. That's the most obvious way of constructing new representations out of old ones. And the corresponding operation is just the sum of the trace functions. So the sum of two trace functions is a trace function. So typically, if V1 and V2 are not 0, then this can never be geometrically reducible. It will have pieces which are invariant. And of course, in any of such operations, kind of the first thing is to know that you can do the operation on trace function, but you should always immediately then think, how does the complexity change? Without control of the complexity, these operations are useless for applications. And what happens is, in that case, it's very simple. Whatever is the definition, the complexity of K1 plus K2 is basically the sum of the complexities of the summand. Very easy operation also is, so there's a twisting operation which on V would be denoted by alpha power deg tensor V, where alpha is modulus 1. So whatever that is, this is an operation which maps k to an alpha k. This, because alpha is modulus 1, it sends geometrically reducible to geometrically reducible, and the complexity doesn't change. Then if you go to the dual representation, then one shows that the corresponding operation is just complex conjugation. This is actually quite deep. At the missing points, to check that the complex conjugate is the right thing is a deep fact due to Hofer-Gaber. But this works, and the complexity doesn't change. And I should say that one could work without the missing points and just add them afterwards. So the fact that it's a deep fact is very convenient, that one doesn't have to make changes when taking conjugates, but it would not be a massive problem. It was not the case. Okay. Change a variable. So suppose you have a gamma in PGL2 of Fp, which acts on P1 of Fp, let's say of Fp bar, then k of gamma x is a trace function. So this uses the fact that, so there is a natural extension of the trace function on Fp to P1 of Fp. So one can always speak for any given trace function of what is k of infinity in a completely canonical way. So the same way that here I said that KL2 of infinity is 0, this is not just a convention, this is the right value. In other cases, it might be something else. So natural extension of k to define k of infinity. And the complexity of k of gamma x is the same as the complexity of k. So in particular, k of ax plus b for any fixed a and b with a non-zero is also a trace function. One can actually do other operations. You can also change variables by a polynomial and not just by homography, but for the moment I won't go into this. With this, yes. Yeah. And you can prove it with the Diophantine criterion. When you change this variable, the sum is basically the same, except you might have switched infinity and the pre-image of infinity. So the sum has changed by a bounded amount between the two. And it's also completely obvious once one knows in the formalism, it's just, I guess, precomposition by a homomorphism of the group, automorphism of the group. So I should say, here also it preserves irreducibility. So this, so when I put a star, this means it preserves irreducibility. And it also preserves non-geometric irreducibility if you want to think about it. Okay, now something that's just a little tiny bit more complicated. I guess it's 6, yeah? So what about products? So products is a bit more complicated because, so of course what you want to do is if you have two representations to map it to the tensor product, so the characters should multiply. However, just like the product of two Dirichlet characters which are primitive might not be primitive, think of Legendre times Legendre is the trivial character. So here you get something which should be K1, K2, but is not quite. So this is again a technical issue which has to do with the choice of formalism. So either you want to have analogs of Dirichlet characters or analogs of primitive Dirichlet characters. Both have their advantages. I prefer the primitive one, and so I have to change a little bit sometimes the product. So there exists a set S in Fp of size bounded by the sum of the complexities of the two terms in the product, such that and a case 3 trace function such that case 3 of x is k1, k2 outside of this bounded set. And, well, the complexity of case 3 is bounded. I have to remember something like, okay, let me write 10 c1 squared, c2 squared. Don't remember if it's correct, but it's almost certainly. So it's only bounded in terms of complexity of k1 and k2. And because k3 is bounded by this quantity, L infinity norm is bounded by this quantity, k1 times k2 is bounded by c1 times c2, because L infinity norm is bounded by complexity. At these boundedly many points where the two functions don't coincide, the difference is also bounded. So for x in S, k3 of x minus k1 of x, k2 of x will be bounded by 1 depending on C1 and C2. So you can write down the inequalities that come out. It's not very important. So for all purposes, that means that the fact that it's not quite a trace function is just a technical nuisance, just like taking products of Dirichlet characters, which is not always primitive. Okay. Right. Now, something which is not quite formalism, which goes a little bit deeper in explaining what is the complexity, it's the issue of ramification points. So a Dirichlet character has a conductor, and I said the complexity is an analytic conductor, but it also has some features similar to the fact that the primes dividing a conductor for a Dirichlet character is places where something strange is happening. And here we have something similar. So one defines a finite subset Okay, so this is an invariant, I should say, of really of the representation. So I should say we start with the rho. So given a representation rho, there is a finite subset of so-called ramification points. I will call it S rho, singularities. This is most naturally seen as a subset of P1 of FQ bar. So it's either of FP bar, sorry. So it's not necessarily an element of FP. Could be something which lies in a extension, or it could be infinity, such that, so how did I, right. One way of phrasing it is this way. So first, the size of S rho is again bounded by the complexity. So that's the second ingredient in the complexity. So there's the L infinity norm, or if you want, the dimension of V. And there is this set of singular points. And if the sum of these two invariants was enough to bound the complexity, this would be great. So it turns out it's not the case, but we'll see that next week. And what is the meaning of these singular points? So one way of saying this is that for x not a singular point, so unramified, I'm going to phrase it this way. So K of x can be written as the trace of a unitary matrix of size dimension of V. So K is the trace function associated to. I guess I have to let this one go. Okay, so if x is unramified, so x is in FP but not ramified, then K of x is the trace of a unitary matrix of size dimension of V. Okay, so in particular, of course, this recovers the fact that the L infinity norm is bounded by the dimension, which is bounded by the complexity, at least for these unramified things. So it implies absolute value of K of x less than equal to dimension of V less than equal to complexity. And so this would not be so useful, but if x is in S rho, this fails more precisely. So K of x is the trace of a matrix of strictly smaller size, so really strictly smaller, and whose eigenvalues are all of size at most 1 over square root of p. So the eigenvalues drop. Actually, are all the eigenvalues? No, certainly not. So one of which at least. So not one of which, so one eigenvalue of which so drop in modulus of the eigenvalues. If you know a little bit about modular forms, this is very analog to the fact that at the ramified primes, the Satake parameters drop in modulus. So Ramanujan-Peterson conjecture says modulus is 1 for all the local parameters at unramified primes, and at the ramified primes, it is known that actually it drops in modulus. So this, in this case, because it's not necessarily reducible, it could be that some eigenvalues remain of modulus 1. But that's the main point is this. And from this, or from other fact, it's easy to check then that S rho is an invariant of rho up to geometric isomorphism. And therefore, this gives us a way sometimes to say that two things are not geometrically isomorphic simply because we know what is this finite set. And if the two sets are not the same, they are not geometrically isomorphic.
So where does this dimension less than complexity come from?
This is something I said. So in the way we define the complexity, so we actually define the complexity as the sum of three terms: the dimension of the representation, the number of singular points, and an invariant of wild ramification.
Oh, so it's not just the analytic conductor.
No.
If you took just the analytic conductor, what problems would you have?
So if you just take the analytic conductor, then it would not be a height.
In what, like which thing would?
So typically, for instance, all hypergeometric sheaves in the sense of cats would have the same conductor. And some of these have unbounded rank and so on. So it depends what you mean by analytic conductor. So it's not the Artin conductor, for instance. One needs a little bit more information.
Yeah, so hyperclusterman sum, they have rates at 1 over the index of the Clusterman sum. So yeah, less ramified.
So they have unbounded rank and
Yes.
Yeah. So we've been told by Will Sawin that so there's a better thing to take, which would be actually I'll state it later because I need something else. So there are more algebraic versions of the definition of the conductor, but we cannot just rewrite all our papers for the moment. So we're keeping the old one up until the point where it's really not possible to ignore a better definition. For analytic number theory, this is not the issue. So, okay, so to repeat a little bit. So we have one extra invariant, this set of singular points. So let's go through the examples and say what we can say about these singular points. Case 1, so for additive characters, this is included. So there could be some issues for small prime, but it's including the set of poles of F for EP of F of n. For multiplicative characters, it's zeros or poles of F, and one can be more precise and say exactly which ones are not. So to see an example where it's not equality here, if you have a double pole and a character of order 2, so double pole means you have a factor, let's say 1 over x minus alpha squared, and this is not ramified for the quadratic character. So if you can be more precise, but it's enough for the moment. For Clusterman sums, it's 0 and infinity. And for the case 3, k of n, okay, so for counting function of number of solutions, again, I think there might be some things happening which I don't remember exactly, but it's only included in the set of critical values of f. So critical values means you look at the zeros of the derivative and the image of f under this. So this is a set of f of zeros of f prime. So when I say there could be issues, typically if the polynomial has degree divisible by p or something, you could expect strange things to happen, but one can be more precise. This is just to begin with. And for the Legendre curve, so this k of n, which counts the number of points on the Legendre family of elliptic curves, this is 0, 1, infinity. So which typically here you see this is the situations where things behave a little bit strangely. So here if you take n equals 0 or 1, you have a double root, and infinity seems to be always a little bit stranger. Infinity is not always, so here I should, no, it's actually. So here if you have a rational function which is regular at infinity, like 1 over x, then this is not a singularity of E of 1 over x, for instance. Okay. So with this done, we can go back slightly to what we were trying to do with the Friedlander-Iwaniec sum once it's transformed into a sum of KL2s. So back to Fi ABP. So this was the sum of, after transformation, T in Fp, KL2 of 1 over T, KL2 of A over T plus B. Okay? And now we can use this extra information to see that if B is non-zero, then K1, so this was, or K tilde 1, is ramified at 0, but not K2, K tilde 2. So for t equals 0, it's like KL2 of infinity, and KL2 at infinity is ramified. This is example 2 above. And for t equals 0, we have A over B, which in that case is just an element which is neither 0 nor infinity, so it is unramified. So they are not geometrically isomorphic. So there remains the case B is equal to 0 and A different from 1, where we expect they are not geometrically isomorphic, but it's not obvious. In that case, both are ramified at 0 and infinity. Actually, I think in the paper they don't need that case. So if I remember right, for some reason, I will have to check. I think it's enough for the Friedlander-Iwaniec argument to deal with the case where B is non-zero. I don't know. I have to check that. Anyway, so next week we'll see further invariants which allow you to distinguish KL2 of 1 over T with KL2 of A over T and show that when A is not 1, they are indeed not isomorphic. So this is still not clear with the amount of information we have. Okay. Now in the last few minutes I want to introduce one last piece of formalism which is much deeper than what I've already described and indicate some other application, natural analytic application. So I guess it's number 7. Yeah. It's the Fourier transform. Now this is extremely deep, if only because there's no analog of this at all for classical modular forms or for modular forms over number fields. So this is an operation that makes sense over trace functions and which has an incarnation at the level of the underlying representations, but for which there are no analogs over number fields. So it's really a deep construction, which is again due to Deligne, and which was studied extensively by Lomont and by Katz and a few others. Okay, so here's the thing I want to say. So let K be a trace function. Yes?
I think once you have eliminated the case B non-zero, you are done, because then you change variable to T goes to 1 over T there, and then you can evaluate.
Yes, that's the way to do it. Yeah, I remember now. Yeah, you're right. Yeah, so you can check if B is actually 0, you can actually compute this by Plancherel formula, essentially. Yeah, thanks.
So you, when B is not 0, you cannot make the changeover. Yeah. Otherwise, you.
Yeah. So these two, I mean, it will be clear. So this is the, if you replace T by 1 over T, this will be Fourier transform of characters, one-dimensional thing, and you can execute this sum when B is equal to 0. That's actually the way Friedlander and Iwaniec do it in the paper. Okay, which again exemplifies the fact that one should not just blindly try to apply the formalism. I mean, your analytic instincts and your analytic knowledge can always or often still be used even in situations where algebraically it looks a bit iffy and not obvious. So one can also prove it algebraically, of course, but one requires then a little bit more work. Okay, thanks. Okay, so let K be a trace function mod P. We need an assumption. We need that either it's geometrically reducible and not an additive character, or I could say that with no factor. So when I mean factor, I mean summand of the type alpha times EP of AX over P in its decomposition. So if k is geometrically reducible, that just means that k is not proportional to this, or it's not geometrically isomorphic to So probably speaking, this has to be a statement at the level of the underlying representation. But for small complexity, it's the same as saying that if you decompose it as a sum of trace functions which are geometrically reducible, there's none which is just proportional to an additive character. And the reason we need this is simply that the Fourier transform of an additive character is a delta function, and delta functions are not well handled by the formalism I'm describing. So there's another formalism which can do it, but it's even more abstract, and I don't want to go into this. Okay, so for instance, any of the examples we've seen has this property, including case 3, which is not entirely obvious, but it is if the degree of f is less than p, provided f in that case is not of degree 1. So all the examples here work, except this when f is of degree 1, or sometimes this when the degree of f is larger than p, larger or equal to p. So it's a very generic assumption. So then I define the Fourier transform of k as the map, the function on fp, which sends h to, so we normalize by 1 over square root of p. It's the most natural in this case. So I think at first we were using just a naive sum, and then Paul Nelson pointed out that it was much better to be unitary in this case. So it's just the usual Fourier transform. We've taken the bad habit of writing E of an over p instead of minus an over p. That's from Katz, because that's what he uses in his books. That's an h, yes, thank you. And there's an h here. Yeah, h n over p. So it's just the discrete Fourier transform with this normalization. So the meaning of the normalization is that when there's square root cancellation, this will be bounded. So it has a chance of being a trace function of something with bounded complexity, and this is what happens. So there's a theorem. It's really deep. It also uses the Riemann hypothesis in a fairly strong form. So if so there exists a representation ft of rho such that the trace function is exactly that, including all the bad primes. There's no change has to be made. So this is the line, minor addition, an epsilon-esque addition that was not in the literature, but was not particularly hard to check based on the work of Lomont in particular, is that, as I said, this would be nice theoretically, but not very useful for analytic number theory unless we control the complexity. And from the work of Lomont, which says lots about the invariance of the Fourier transform, it's not hard to check then that the complexity is controlled. And what we got was 10 complexity of k squared, which is probably not best possible, but certainly is enough for applications. Okay, so that's...
You don't want to be pedantic and put a -1?
No, I don't want to be pedantic, because I didn't do it for the Klusterman sum, so... yeah, the most proper way of defining this would have a minus sign. Okay, so examples.
Why is that?
Well, it's an H1. It's a trace on H1, and it has to be an alternating sum. Yeah, I've not mentioned the word cohomology a single time, except like 2 seconds ago. Okay, oops, I'm already over time. Do I want to say anything that's... Right, let me state an immediate corollary of this, which actually in principle goes back to more or less the thesis of Philippe, is that you can have Polya-Vinogradov bounds for any trace function. So let K satisfying, so a trace function which has a Fourier transform, as in the sense above. Also, I modulo p is any interval, so meaning the projection modulo p of an interval of integers of length strictly less than or equal to p. Then what you deduce from this in the standard completion method that was explained by Terry, for instance, is that you get, well, the conductor of the Fourier transform, so C will be the complexity of K, so 10C squared, square root of P, and log of 3 times P. So we actually had a paper where there was a big O symbol, and then Serre sent us the remark that you could replace the big O symbol by less than or equal to log of 3P. So we had less than log P, but it doesn't like implicit constants. Okay, so, and this is completely straightforward. You just apply, you write this as, you apply Plancherel formula. So this will be the sum of the Fourier transform of the interval, characteristic function interval, times Fourier transform of K. You bound the Fourier transform of K by its L infinity norm, which is bounded by the complexity, which is at most 10C squared. And then you sum the Fourier transform of the interval, which is, without normalization, at most square root of P times log of 3 times P. And that's the proof. Okay, so I'll stop here for today.
Any questions? Thomas?
Can you say something about the irreducibility of the Fourier transform?
Yes, so it's, in this case, it's completely obvious from the Diophantine criterion. Fourier transform, the way I define it, is unitary, and therefore the L2 quantity that you want to control is the same. So if K is geometrically reducible, so is the Fourier transform. And of course, it can also be proved differently, but from the analytic point of view, there's no mystery in this fact. It's a very useful fact, because the Fourier transform of something of rank 1 can be quite complicated, can have arbitrary rank. If you have an arbitrary rank object, it's sometimes hard to check that it's irreducible, but if it's Fourier transform of rank 1, it's obvious. On this side.
So in the example 3, is it a theorem that if you have a non-singular critical value, then it is included in S row?
Yes, only at least if the degree is coprime with P. If the degree of F is less than P, let's say, strictly less than P, yeah, that's certainly the case.
Okay, so there is no more questions.
Okay, so again, I've written down on the blackboards the Riemann hypothesis and the basic examples that I've used. And so today I want to begin by saying a bit more about the conductor of trace functions or of the associated representations. So and give in some sense what's the precise definition without going too much into the details, and explain why we need something a bit more than the two informations we already know. So suppose you have a trace function k mod p. So you don't need to assume that it's geometrically reducible or anything like that. So it's associated to a representation rho. So some analytic representation or whatever. And so the complexity is really an invariant of the representation. For the trace function itself, you would just take the infimum over all possible rho with trace function k. So we already know two components of this. So we want to measure the complexity, and we saw that, I said that we take first the dimension of V at least. Then there is this singular set, so it's a subset of P1 of Fp bar. Which is a finite subset, which is an invariant of rho, and you have to take these two. And this is not enough, so what I'm going to do is going to tell you what is the definition and then give an example to show that these two components, which are easy to understand and which are the obvious invariants, are not sufficient to get good properties of the conductor. So you need something else, which is the way we define it. It's a sum of contributions corresponding to every singular point of an invariant called the Swan conductor at X of the representation. So where Swan X of rho is an integer, non-negative. So measuring what's called wild ramification at a singular point. So it is sometimes 0. Then one speaks of tame ramification. But not always. So I'm going to give an example that shows that if you want to have a statement like the Riemann hypothesis, so if you want a statement like this to be true with an invariant, a complexity invariant, it would not suffice to define just the dimension of V plus the set, the number of singular points. This would not be enough. And then I'll give a few examples, but not much more. So this is an invariant that's quite subtle and delicate. And in many applications, if you don't know the conductor and you need to estimate the conductor, this will be the hard part to control. Because it's really a subtle algebraic invariant of the representation, which is not so accessible from purely Diophantine or concrete properties of the trace function. So why do we need this? Okay, so there are two reasons. So the first one is if we want the complexity to be some kind of height, so what do we want? What does it mean to be a kind of height? That means we want the sets of rho such that the complexity of rho is less than x, and let's say rho is geometrically reducible, modulo geometric isomorphism is finite for every x. So this is the more precise form of what I described in the first lecture. I mean, I said this this complexity has a height property. At that time, I had not said what it means to be geometrically reducible. So this is the right thing to do. These are the building blocks of all trace functions or all representations. And you have to take modulo geometric isomorphism because otherwise multiplying by a scalar with absolute value 1 gives you infinitely many which are geometrically isomorphic to a given rho. But if you do it this way, then actually it's a finite set. So this would not be true if you just take the dimension of V plus the size of the singular set. Then we have so if you take the set of all rho where so rho is geometrically reducible, but the dimension of V plus the set of singular points is less than x, so modulo isomorphism, geometric isomorphism as above, then this is not finite. And that's simply because it contains all kind of over all rho associated to trace functions of the type EP of f of x, where f is a polynomial of arbitrary degree. Okay, so when one does this type of correspondence, it's possible to do it in such a way that it's essentially injective from fp of x to the set of representations. So I won't go into details. And here the point is that the dimension of V for all of these will always be 1, independently of f. And the singular points will always be restricted to infinity, independently of f. So this object, a polynomial, is only really strangely behaved at infinity. Then when we take the exponential, every value which is not infinity behaves the same. So intuitively, it's somewhat clear that this is the only point that could be singular, and in fact it is, at least if f is non-constant. So this last part would be for degree of f at least. Okay, and so we have infinitely many polynomials because the degree is unbounded, and all of them have the same dimension and same singular set. So this set is infinite, but we want the height property to be true. So we need something else that, in this case, has to take into account the degree of f. So what's missing in this case is very clear. If we bound the degree of f, then we have a finite set, growing with p to the power d, but nevertheless finite. So here, so we miss here a bound on the degree of f, and it is a fact. So once the Swan conductor is defined rigorously and so on, we have that the Swan conductor at infinity of such a rho, let me maybe call it rho f, so that associated to this will be the degree of f, at least if the degree is prime to p. And in any case, it's always at most the degree of f. So the Swan conductor of an additive character of a function will always be at most the order of the pole of the function at the singular point. So in this case, the pole is at infinity, so it's the degree. And there's equality if they are coprime with the characteristic. So, and the second example is in some sense similar, in that the issue will also be of the same type, that there's additive characters of polynomials with unbounded degree. But it's more concrete in the sense that you might say that, okay, this height-like property is nice, but it's not the essence of what we want to do in analytic number theory. So this is much more important. However, this would fail with a conductor defined just as the sum of the dimension and S rho, essentially for the same type of reasons. So consider an integer k at least 1, such that p is congruent to 1 mod k. Or consider k and then look at all the primes congruent to 1 mod k and define k of x to be EP of x to the power k. So then, if you look at the sum skp, which is just the Gauss sum built with this EP of xk, so it's a generalization of quadratic Gauss sums, x in fp. So it's a generalization of the fact that the quadratic Gauss sum is the same as the quadratic Gauss sum for the real character, that this, under this condition, you detect the fact of being a case power using characters of the quotient group fp star modulo fp star to the power k. There are k such characters. One of them will give a trivial contribution, and the other ones will give k minus 1 Gauss sums. So this is, in this condition, the sum of k minus 1 Gauss sums. So by Gauss sums, I mean things like EP of x, chi of x, where chi will be of order k and non-trivial. Okay, and under this condition, of course, we know there are such characters. There are k of them and k minus 1 non-trivial. So it's not easy, not hard to find, to deduce that if you take, so if you try and do the inner product with the constant function 1, so as p goes to infinity, p congruent to 1 mod k, then this will be k minus 1. Normalized by square root of p. Okay, on the other hand, the associated dimension of, which I call vk, plus the set of singular points is again 1 plus 1. for the same reason as before. It's an example of the previous construction with f a power. So dimension is 1 and there's just one singularity at 1. So you see that an estimate like the first part of the Riemann hypothesis does not hold with C1 and C2 replaced by just the dimension plus the number of singular points. So RH would fail with C of k I replaced by dimension plus number of points. Okay, so it's clear that this is geometrically non-trivial. This is not constant as x varies. Well, maybe it's constant with p is equal to 2. I don't know. Not even that, I think. No, because it's 1 at... Yeah, it's E of 1 over p for x equals 1, and it's 1 at x equals 0, so this is not proportional to a constant. So it is geometrically non-constant, geometrically not isomorphic to the trace function 1, so we can apply the first part of Riemann hypothesis, and this would not be true without this assumption. Yeah?
So in both of these cases, the dimension of V is
1.
in your example, so suppose that we restrict this set to dimension of V greater.
That doesn't work either. So it would fail, for instance, with hyperclusterman sums when R goes to infinity. But these are the simplest examples. So I don't want to go into more details about this because in some sense this is the trickiest part and analytically it's the one that's the most painful. So one tries to avoid it as much as possible. Again, if you're working with well-known trace functions, meaning those you would find in a table or in a list of examples, then that means that these tables are only good if they include information on the Swan conductor. So this is known. So let's go back to the examples. So here, for additive characters, as I said, if f is a polynomial, let's say, well, so if x is a pole of f, then the Swan conductor at x is at most the order of the pole, with equality if it's coprime to p. So that's generalization of what I did. So we see here the feature that the Swan conductor is local in some sense. Here it only depends on the order of the pole of f at this point. It's local in a more precise technical sense that is sometimes useful. So here the singularities are zeros and pole of f, but all the Swan conductors are 0. So multiplicative characters in this sense are easier to handle in some cases because they are tamely ramified everywhere. So all the Swan conductors are 0. Hyperclusterman sums, so singular set was 0 and infinity. It's tamely ramified at 0. So Swan conductor at 0 is 0. And at infinity, it's 1. Okay. Here, let's say that P does not divide the degree of f. Then the Swan conductor at every singular point will be 0. So point counting functions are also tamely ramified. And for the Legendre family, this is also Swan at 0 equals Swan at 1 equals Swan at infinity is also 0. At least if P is at least 5. And this actually is related, so if you know a bit of the analytic theory of elliptic curves, the exponent of the conductor of an elliptic curve defined over Q is always bounded by 2, at most 2, except for primes P equals to 2 or 3, and this is the same type of behavior. So the fact that the conductor has exponent bounded by 2 is also a feature of tame ramification, and in the case of trace functions, this goes into this type of properties. So this is going to be typically true for any family of algebraic varieties if the equations are defined over Z and fixed, and P goes to infinity. For P large enough, then everything would be tame. If you just count the number of solutions. Okay. So this is all I want to say about the conductor, at least for today. Maybe tomorrow I will have a little bit more in one of the applications I want to discuss. So what I'm going to do now in the remainder of today and tomorrow is give some kind of survey of some of the applications, trying to highlight some of the features, how one uses the Riemann hypothesis, and how it meshes up with analytic number theory. So some applications. So first part. So in the first part, I will discuss the results in a series of papers with Fouvry and Michel. Which is where we started working with these objects, where we are trying to understand their correlations with automorphic data. So the motivating problem, or one motivating problem, it's not quite exactly where things completely started, but it's something that I'm going to take as motivation, is to understand, so given a modular form F on a congruent subgroup, let's say gamma 0n. So this is classical modular forms, subgroup of SL2Z. But it could be a mass form or holomorphic. So we have applications in all cases. Or it could in fact be Eisenstein or cuspidal. Again, there are applications of both cases, and I mentioned some of them. So it's not so important for us whether it's Fourier coefficients or Ecker eigenvalues, but let's assume that it's Ecker eigenform with Ecker eigenvalues lambda f of n at least one. So normalized so that the mean square is about 1. So lambda f of n squared is equivalent to a constant depending on f times x. So the usual analytic normalization. So we consider fix subprime p, which will then tend to infinity, and the trace function k mod p we consider sums like S, F, K, P, which is smooth sums obtained by comparing lambda f of n, so an automorphic arithmetic function, Fourier coefficients, against this trace function, which we view as a function defined of all the integers by periodicity. And the critical length is about p, which is natural because k is periodic modulo p. So we take a smooth cutoff at n over p. So this is a sum which you can think of as being between 1 and p, but with a smooth cutoff. And the estimates will be such that the sum could be a little bit shorter, p to the 1 minus some small constant. When n gets extremely large, so if the length was, let's say, p cubed or p4 or something, then you would just use periodicity and replace this as a sum over a of k of a times the sum over integers congruent to a, and apply known results on Fourier coefficients in arithmetic progressions to handle this type of sum. So where p is a smooth cutoff, which in fact can oscillate a little bit, but the first idea to have in mind is the usual picture, which I think Henrik Ivanets has drawn on his blackboard every single time I've spoken with him, and which is the right way of doing these things to avoid analytic issues until you really need to handle them, if you need to handle them. So we start with that, and we want to obtain estimate. So the philosophy is the usual one, that unless these objects are correlated in a strong sense, there should be some cancellation in the sum. So lambda f of n is roughly bounded on average, at least in mean square. K of n we know is actually bounded by the conductor. So if the length is about p, you can expect, in good cases, to get square root of p cancellation. And we try to get some cancellation at least, which would show that automorphic data cannot be modeled in an easy way with this kind of trace functions. So the goal is cancellation. So this can be seen as a challenge. So we think we know something about automorphic forms. We think we know something about trace functions. Can we actually show that we know something about them? Or it has applications. So I'll start by discussing this kind of as a challenge, and then we'll see the applications. So a basic example that you can have in mind, or two examples. So actually the first one will immediately show that it's not a purely academic game. So a simple example is a multiplicative character. So k of n is chi of n, where chi is mod p and non-trivial, let's say. It's a Dirichlet character. Then because the length is p, detecting cancellation in that case, lambda f of n, chi of n, is more or less the same. So that's the right length because of the conductor of the twist is p squared times n, maybe, if p is coprime to n. So the sum, in that case, SF chi p, controls subconvexity for the twisted L function at 1f. In level aspect, of course, with respect to. Meaning that if we get power cancellation, then we will get some kind of subconvex estimate for these L functions, which are very important in analytic number theory and in applications. So kind of one of the guiding examples we had. So at first we had no idea what would come out. So I don't mention the example of additive characters. The example of additive characters is one that's very well known due to, there's an estimate of Wilton, which is easy. But the first example we kind of used as trying to see whether we could do it. So our challenge was to try and do it with EP of n bar, so EP of 1 over n modulo p, which is kind of a building block of Kloosterman sums. Can we show that the sign changes of the inverse modulo p are sufficiently random or sufficiently independent of, let's say, the coefficients of the delta function of Ramanujan? This type of basic question, which is not easy even for this very special case. So it was one challenging example. Okay, and then, okay, so maybe I'll just, in fact, give another example immediately. So this is where we vary the k. But there's also, quickly, there are special cases of automorphic forms where you take, for f, an Eisenstein series. So let's take the Eisenstein series at 1/2 plus it, where t is a real number. Then lambda f of n is the sum of a over b to the power it, where ab is equal to n. So strictly speaking, for t equals 0, we have to take the derivative, because this is literally 0, but I'm ignoring this. So for t equals 0, the Fourier coefficients are the divisor function, and therefore you get the type of sum that we're looking at for e 1/2 plus it, k and p is a sum over integers mn, at least 1, of k of mn, v of mn over p. So this would be for t equals 0. And in general, you have m over n to the power it. Okay, and these are very interesting because they give you special bilinear forms when you're trying to apply combinatorial identities to detect primes. And the presence of the it and the fact that we're going to get uniform estimates with respect to t to some extent allows you to balance the size of m and n in certain intervals. So you get special bilinear forms, but in great generality when the coefficient is k of mn, where k is a trace function. So this will be the application later. Okay, so now I'll state the results and then say a few words on the proof, and in particular highlighting what is used about trace functions in this proof. So it will depend on the Riemann hypothesis, but it's interesting to see analytically how it's used, how it comes up. Okay, so theorem. Okay, so there exists a positive absolute constant. I think we checked it can be taken to be 9, but I'm not sure. Such that for every prime p, for every k mod p, let's say geometrically reducible, although this is not strictly speaking necessary, but so in the Eisenstein case, so suppose t equals 0, you take the Eisenstein case, you have sum of d of n times k of n less than p essentially. So if then k is a constant, you're not going to get cancellation. Sum of d of n has no cancellation. And if k is an additive character, it also doesn't quite work. So we assume that k is not an additive character, EP of an, in the special case if f is an Eisenstein series. So in the cuspidal case, there's no condition. And in the Eisenstein series case, this is the only exception. So when I write this, you always have to think that the representation associated to it is not the representation associated to that. Or you can think that k is not proportional to one of these, which is a weaker condition. Okay, then, so if I do this sum, so we get cancellation. So for every positive epsilon. So I write that the implied constant depends on the test function v. They depend in a completely explicit way, so we can actually play games with v to get some oscillating v's or slightly shorter intervals and length p. But I don't write this explicitly. So in terms of k, it depends on the conductor, but polynomially. And the exponent is not terrible, but I don't remember exactly if it's 9 or slightly bigger. And then with respect to p, we get cancellation. And the cancellation is completely uniform, 1 minus 1/8 plus epsilon for every positive epsilon. Okay. So what is striking, one of the striking things at least, is the complete uniformity of the exponent in the gain. So we always gain 1/8 independently of the complexity of k. By complexity, I mean how complicated it looks when you write it on paper. So to say that this is efficient, it means that the C of k, the actual conductor, has to be bounded or growing relatively slowly, so that ck to the power is less than p to the 1/8, okay, because the trivial bound is roughly p. But for instance, if you take any of these examples with fixed polynomials of rational functions f here or there, or here fixed r, then you can apply this theorem for every one of these, and the exponent gain will be the same. And the fact that this gain is uniform ultimately just comes from the fact that the Riemann hypothesis is just as uniform. So the Riemann hypothesis has code of p independently of which shape of k you take. Okay, so before were known, so of course the subconvex bound was known, and the exponent is the same as the best which is known in that case. Is also due, I think, first to Bikovsky, and then was generalized. So this is for prime moduli. The exponent is known for subconvex bounds, even for general moduli. And also there's this paper of Blomer and Arkush. So it's also known, as I said, for additive characters, for cuspidal case. EP of an, that's due to Wilton. This is an old estimate. And I guess one can interpret various statements in the literature as extremely special cases, maybe with slightly different Karian EP. But apart from that, essentially nothing was known or had been tried. I guess Philip's paper with Venkatesh can be interpreted as giving some of these for Fourier transform of a multiplicative character. Yeah, I guess which is the same. Okay, so this is the first theorem. Now, as I said, because we can handle the... So here also one doesn't see the dependency on T when you take Eisenstein series, but it's under control, it's polynomially bounded. So we can use this estimate for Eisenstein series, interpreting it as special bilinear forms, together with extra ingredients coming from the Polya-Vinogradov method and combinatorial tricks and identities like his Browns to handle sums over primes. So again, there exists a positive A, such that for all P, for all K, trace function mod P. Again, I assume for simplicity geometrically reducible with, so in that case, for sums over primes, we have to exclude a bit more. So it cannot be a multiplicative character times an additive character. Okay, so in that case, it's only clear why we need that for multiplicative characters, because the estimate I'm going to write would be a quasi-Riemann hypothesis if we could handle multiplicative characters. So just like Vinogradov's old ideas involving bilinear forms and so on, this breaks down when the function is multiplicative, and chi of n is roughly the only trace function which is actually multiplicative. Okay, and the EP is not so clear, but it also is needed. Then we can do sums over primes, so sum of lambda of n, k of n, v n over p. And again, we get, so with implied constant depending on epsilon and on v in a well-controlled way, polynomial bound in terms of the discriminant of the conductor, and then we again gain something times 1 minus 1 over 24th plus epsilon. Okay, so again, the exponent gain is completely uniform independently of what the trace function looks like. It only needs to be a trace function. There's no lambda here. We pass from automorphic data through the spectrum, the fact that we have Eisenstein series, which allows us to control divisor sums like that. We can actually put the lambda of n. So adding an additional lambda f would be another problem which we don't know how to do. So there is no dependency at all on Ramanujan-Peterson type approximations. This is all valid for mass forms and holomorphic forms uniformly. Yes?
If you replace the smooth wave by like a sharp cutoff, do you get any power saving?
Yeah, so we just divide the saving by 2. So we get 1 over 16 for theorem 1, and for theorem 2 we get 1 over 48. Okay, so let me say some highlights of the proof, not really even ideas, because it's really quite long altogether. So focusing on where the trace functions are used. So there's a lot of analytic number theory involved, but I focus on the trace functions. So on the analytic side, so I begin with theorem 1. On the analytic side, we use amplification. So we view f, so f was of level n, we view it as a cusp form or modular form of weight p times of level p times n, where p is the prime corresponding to the trace function, and we amplify in all the space of forms of level pn in forms. So this is an idea that has been used also in particular by these papers of Bikovsky and Baumar-Koch, and also been used by Ivanets very effectively to amplify certain results. So in some sense here we use, so it's this idea of putting f of level Pn is very natural a posteriori, but a priori one has to think about it. So that's the analytic step. then once we amplify, so we use Kuznetsov formula. We could use the Peterson formula in the holomorphic case, but we would then lose quite a lot in certain estimates, so it's better to use the Kuznetsov formula. So in particular, so even if you're only interested in the divisor function, so divisor function level 1, no special features of its Fourier coefficients, we go to full spectrum of level P, including cuspidal spectrum. So we treat the divisor function fully as an automorphic object, and in particular we use cusp forms of level P in order to get, in the end, an estimate for the divisor function, which is sharper than known estimates in the case where we apply it. So even for D of n, divisor function. So analytically, this is the feature. So once you do this, so there are many complicated steps, but you end up with, so we are led to certain exponential sums mod p, or generalized exponential sums, which we call correlation sums of k with respect to gamma. So gamma will be an element in PGL2 of Fp. And this tries to understand the correlations between not k, but its Fourier transform, and the transform of the Fourier transform when you replace x by gamma x. So k hat of x, k hat of gamma acting on x, conjugate where, so k hat is the Fourier transform, which I recall is the sum over y, k of y, EP of xy over p, sorry, xy. At least when x is in Fp. So here you could exclude the value, the pole of gamma x if you want, but it actually works out fine if you add it, since this trace function, as I said, extend naturally at infinity. Okay, and then we're going to play a game. So of course, so k was geometrically reducible, that's my assumption. So Fourier transform, as we said last week, is also geometrically reducible. We make a change of variable, this is also allowed. So k hat of gamma x is also a trace function, and it's also geometrically reducible because the change of variable is bijective and k hat is geometrically reducible. So we are exactly in the situation where we can apply the Riemann hypothesis with k1 is k hat and k2 is k hat of gamma x. And the point is, can we apply the Riemann hypothesis in the sense of, are we going to get result A or result B? And what we need, so we need square root cancellation. However, not always. This is, if we need square root cancellation always, there would be an obvious problem, is that you can take gamma equals the identity and then there's no cancellation. So we are not really fortunate, I think it's just a feature of this type of method that they allow for a small number of diagonal cases where you have no cancellation, with few exceptions, which one calls a diagonal exception. Okay, so then what happens is we balance two facts. So which matrices gamma come into the argument? So on the analytic side, we don't get a sum over all matrices in PGL2 of Fp. We get a sum over some specific matrices of relatively complicated shape, but which have one feature, is that they are not algebraically structured in some sense. They do not form a subgroup. So from 1, meaning from the analytic argument, the gammas to control are not algebraically structured. I mean, they actually form algebraic families, but not subgroups. At least they do not look like subgroups, and one can check that typically the multiplication will not look like it's stable. However, from the Riemann hypothesis, let's try and understand those gamma for which there's no square root cancellation. So meaning, in which case do we not apply this, but only that. So if M is a constant large enough, depending only on the conductor of K, so that it will control also the conductor of the Fourier transform, because, as I said also last week, the conductor of Fourier transform is controlled in terms of the conductor of K. So if M is large enough, then the only possibility to not get square root cancellation with a constant which is M is that this condition fails. So this means the hypothesis here must fail. And so we are in case B. In case B, that means that K1 is proportional to K2. So if gamma satisfies that the correlation sum gamma is larger than M square root of P, then in particular K1, that means K hat, is proportional to K hat of gamma x. So there exists some alpha depending on gamma, such that we have that for every x. Yeah, I should say, I actually changed the notation here. So in the paper, no, that's the right notation, sorry. So we've sometimes changed notation in our various papers, so one has sometimes to be careful with. So whether this should be associated to K or to K hat is not entirely clear. So here I use the same definition as in the first paper. Okay, anyway, so we have this conclusion. This is a consequence of the Riemann hypothesis. So if M is large enough, so roughly speaking, M must be larger than 3 times C1 square, C2 square, where C1 equals C2 is the conductor of the Fourier transform of K. Then A fails, so B must be true. And that means in particular that there has to be this correlation. Okay. Now, the point of this is that this shows that the set of bad gammas, so this condition, defines a subgroup of PGL2 of FP. So the set of bad gamma, meaning those for which star fails, is then a subgroup. Okay, that's quite a strong feature. So if you look in analytic number theory at sets of things where some correlation estimates fail, then typically, I mean, you might have intuitively the idea that they would look like something structured, but you would never usually dream to get something that's actually a subgroup. So here we get an actual subgroup. And then what we can do is we can use the classification of subgroups of PGL2 of FP. They are very well understood for a very long time. And using this, we can show then that they do not mess up the outcome of part 1. So we get a good estimate from part 1 using this kind of fighting between the non-algebraic structure of the analysis and the algebraic structure of the correlation sums. So we use structure of subgroups of PGL2 of FP, which is almost the same as SL2 of FP, to get a handle on the gammas in 1. So meaning that really extremely few of them can possibly create a trouble, so the diagonal cases would be very few, and it's a feature of the situation that very few diagonal cases do not affect the argument. So the nice thing of working, or one nice thing of working in great generality, is that we can have an idea now on what do we need to get beyond the 1/8. So the 1/8, if you think of the subconvexity case, this is the Burgess type exponent, which has never been beaten, as far as I know, for subconvex bounds, at least in level aspect.
4 prime levels.
4 prime levels, yeah. Yes, and we can see clearly in this argument where we would need to have something better. So we would need to understand the variation of the correlation sums as gamma varies, but in the matrices coming from step 1. So we would need to get extra cancellation from these families of correlation sums, which we can expect to hold, but which sounds extremely difficult to get. So for the moment, we haven't really made any progress.
It has been beaten for quadratic characters.
Yeah, but with very different. Yeah. Anyway, so that's the that's kind of the highlights of the part of the ideas that come from the Riemann hypothesis for theorem 1. So theorem 2 builds on this, meaning on the Eisenstein case of theorem 1. So to understand special bilinear forms with smooth coefficients, plus, so on the analytic side, so we need to handle sums over prime, so we use this Brown identity, which is one of the reasons we can get very uniform estimates, because we use it in a quite complicated way. So with many summands, if you remember Terry's lecture, he was taking 10 summands, so the parameter in the Higgs-Brown identity was 10 for the gaps between primes, and here we need to take a number of summands that can tend to infinity with the conductor. So it's quite tricky. And so we need that, and we need a bit more on trace functions. So we need more about the subgroup, so the set of bad gammas in some sense. So here where I just said it's obviously a subgroup. In fact, one can show that it's the FP points of an algebraic subgroup, a linear algebraic subgroup of PGL2, and this turns out to be important in one of the steps here. So algebraicity. Okay, I don't want to go into this. So this comes into the Polya-Vinogradov method. So when we do kind of general bilinear forms, we are led to special cases where gamma is upper triangular, and we need to be sure that there are not too many bad gammas which are upper triangular, and this turns out to be best handled by proving that it's an algebraic subgroup. Okay, so I don't have a lot of time, so I'll mention then a few additional applications. But first an example, so kind of a nice example. So we have a set of bad gamma, so you might ask, well, is this set of bad gamma, does it really exist, or could you just assume that the set of bad gammas is trivial or something? It can exist, and it can be quite hidden and not obvious from the definition. So let me give an example that we actually found purely experimentally, which is a posteriori kind of. I have no idea how we found that, but so it's one of the classical examples that has been studied by Katz. Is to take a Klustermann sum at n squared, then we take its square minus 1. So it's like the symmetric square of the Klustermann sums, but with argument n squared. So if you use the standard notation of Klustermann sums SABP, so this would be SNNP minus P, minus 1 squared. So the fact of taking NN means that if you just have one factor for the Klustermann sums, it's n squared. Okay? So if you do this, then one shows that for this K, if you look at this correlation sum with a factor, with a matrix gamma, this will be of size P. So no compensation, meaning it is one of the bad matrices. For all gamma which are elements in PGL2 of Fp which permute 0, infinity, 4, and minus 4. For gamma in the subgroup H, which is a set of gamma in PGL2, such that gamma permutes. So the singular points are 0, infinity, 4, and minus 4. I mean, this is not obvious. So these are the singular points of the Fourier transform of this Klustermann sum. So this is not obvious, but follows, for instance, from all the work of Katz and Lomont, which allows you to determine the singularities of Fourier transforms. And this, I guess it's an exercise that can be used if you teach Algebra 1. So this group is a diagonal group of order 8. So there's something to do with biratio being of one of the spatial values. So if you have 4 points in the projective line, so usually there are not so many matrices which permute the 4 points, except when they have biratio, which is of spatial type, and this is one of them. So this is actually not so easy to prove. So because the singular points of the Fourier transform are these 4 points, it's clear that the bed matrices must be in this subgroup, because they have to respect the singular points. But the fact that, conversely, if gamma permutes the 4 points, then this sum with the Fourier transform of this scale 2 of n squared squared minus 1 is actually big, is not obvious. So the best proof, so we have 2 or 3 proofs, but the best proof is follows from a result of Deligne and Flicker. So we have a computer algebra proof, and David Ziwina sent us an automorphic proof. So that's a kind of a nice example. Okay, and in the last few minutes, I'll mention some further applications of these, or basically the results in these 2 theorems. So some of these applications are new things. So one is the equidistribution of twisted, some kind of twisted orocycles. So I'll present this quite quickly. So this is the application actually we used as motivation in this PISA survey paper that I mentioned in the first talk. So this is what I was giving that talk in PISA, and I used that as somewhat geometrically accessible even for an audience not of number theorists. So you can find more details by reading the first few pages of this survey. So the idea is really following. So we have the fundamental domain. We are looking at height 1 over p. We're looking at the points w, jp equals j plus I over p, where j is between 0 and p minus 1. So all these points correspond to points in the fundamental domain. Let's call them tau jp in F, so the usual fundamental domain, corresponding points. And the issue is, are they equidistributed? The answer is yes, like this. This follows from bounds on eigenvalues of Eck operators. But what we do is we twist kind of the sampling measure. We twist it with a trace function k of n. So what we prove is then, so for any k, p with complexity bounded uniformly in p, any f, let's say, continuous with compact support on the fundamental domain, meaning on the modular surface, if you average k of n at this point tau jp, p minus 1, and this is j, this is going to go to 0, so if k is not constant, if k is not additive character. And I should say, so geometrically reducible as usual. So a consequence of this, if you use, for k of n, example 3, so counting functions of how many times the polynomial eats a given value. So this will say that instead of taking these points, omega jp for all j's, you can restrict to the subset where j, let's say, is a quadratic residue, or a cubic residue, or of the form n squared or n cubed plus 2, where n is modulo p, and you will still get this equidistribution. So you cannot force these points to lie, let's say, below the ordinate 2, for most of j by just taking those j which are values of a polynomial. This is the type of thing that it means. So it's geometrically quite nice. And it can have applications. So in the paper of Michel and Venkatesh on subconvexity, they explain that in some cases this is also equivalent to subconvexity for twisted L functions. So that's example 1 of application. So interestingly, to prove this theorem, we apply theorem 1 for the Fourier transform of K. Which means that in fact, if you want just to prove this theorem, you don't need to know the existence of the Fourier transform on trace functions, because you end up taking twice the Fourier transform, which gives you back your original thing. So that's one application. So theorem 2 has some applications which we haven't quite written down in detail to low-lying zeros. I won't give any more information of that, of certain L functions. So symmetric square L functions essentially in level aspect. This is because when you apply the explicit formula, you have sums over primes of Kloosterman sums with prime arguments, which is, okay, I raised it. It's the type of sum that we handle in example 2, in theorem 2. So what we also did is D3 in arithmetic progressions, which was used, at least some of the ideas in the Polymath 8 paper. So here the point was we have a much more streamlined proof of the theorem of Friedlander-Iwaniec on getting exponential distribution larger than 1/2 for D3 in arithmetic progressions, with a much better exponent than even Is-Brown's, which had improved Friedlander-Iwaniec. In fact, we don't even need the Friedlander-Iwaniec sum. So it's all incorporated in the statement. In general statements, we can just almost use just generic properties of trace functions again. So it's streamlined and stronger compared with Friedlander-Iwaniec and Is-Brown. But it's only for prime moduli, so it will be a bit more complicated to do for the general moduli. Example 4. So if you're really nasty, you would say, well, you're just either proving non-interesting new results or improving known good results. So let's prove something that's not known. So this is something which is still work in progress with Blomer and Milicevic. So we can handle with power saving a twisted moment of not quadratic, Dirichlet character L values at 1/2. So there's a conjugate squared times twisted L function with a fixed modular form, cusp form, with power saving. So why is that interesting? So, well, if you replace the cusp form by a Eisenstein series, you're going to get modulus of L chi 1/2 4, which was done then by Matt Young a few years ago. And on the other hand, so we can handle this, and we are on the way, or at least we reduce the case where you would have L f chi modulus square, so without this first part, but just a pure cusp form. Second moment, which is a well-known open problem with power saving, we reduce that to estimates for trace function, which we hope one day to obtain. And again, even in the Matt Young case, our proof is much more streamlined. Exponent is much better. So altogether, we have some quite nice applications, I think, of this. Okay, so I'll stop for today.
Questions? Comments?
Is it hard if the trace functions are not geometrically reducible?
No, I mean, I just put it, so in the proof it's useful because you see these correlation sums are not linear. So, but in fact, the estimates, the final estimates are linear. So you would just decompose and apply it to every component.
Another question?
Okay, so
Okay, so so once more I've written the Riemann hypothesis so that we can see it when we're going to use it. So I'm continuing with another type of applications. So I've chosen something which is really something of a case study of a type of sums that turns out to occur quite frequently in applications and which goes beyond the simple application of the Riemann hypothesis. So we need to learn more about the trace functions in order to study certain types of sums. So these are sums of products. Not some products, but sums of products. Okay, and this is not contained in the survey we wrote for PISA. So this you can find in a kind of semi-survey paper, which is called a study in sums of products, which is on my web page, and I think it's on arXiv. Okay. So what is the situation? We want to study sums of the following type. So for applications in analytic number theory, we, maybe not often, but we sometimes, or let me say often, need to bound sums of the following type. Or to understand, sometimes we want more than just bounds. So it's a sum of a finite field, Fp, and instead of having just one k1 of x times k2 of x conjugate, we have finitely many functions, called m the number of them. And I'm still going to put another one, an m plus 1 factor, which I will call L of x conjugate. And the reason I'm writing it this way is that typically this plays a different role than the ones k1 up to km. So m is at 3. So let me say m is at least 1, although m is 1 or 2 can often be handled with just the Riemann hypothesis. Ki and L are trace functions, and in applications we assume that we've already managed to reduce to geometrically reducible cases. So we also assume that we control the conductors, complexity of all factors being small. So typically P is the main variable. Everything else may depend on P, but the complexities will be bounded uniformly in terms of P. Okay, so let me give examples from the literature. So m equals 2 and L equals 1, the constant function 1, is essentially the situation of the Riemann hypothesis. So C are H, and yesterday I gave examples, and there are countless examples in the literature where we have sums like this which are exactly tailored to the application of the Riemann hypothesis. So I'll concentrate on example where m is at least 3, and make a small list. Kind of an old one is in the proof of virtues. So it's a bit hidden because it's applied in the case where the ki's are characters of rational functions, and so you can glue them together in a single thing, but the way they are formed is really by taking a I power of k of x plus ai, and then you get a product of things. So you have something like ki of x is a multiplicative character of x plus some shift ai, and L of x is 1, typically. So this case can also be done without knowing more than the Riemann hypothesis, because the tensor product of one-dimensional things remains geometrically reducible. So this will be extending this to more than more complicated situations. So that's maybe one of the oldest ones. case 2, a relatively old one, is in a paper of Fouvry, Michel, Riva, and Sarkozy, which has to do with pseudo-randomness of some kind. And here, so they have M arbitrary, if I remember right. The KIs are either Klusterman sums or symmetric powers of Klusterman sums. I don't remember, do you do arbitrary type of Klusterman sums or just KL2? Just, okay, so it's something like symmetric powers of KL2 of some AI times n. So I didn't define the symmetric powers. If Ki is 1, this is just KL2 of AI times n. So multiplicative shifts of Klusterman sums. And L of x is then an additive character. And this is used to kind of control the same sums, but over shorter intervals with the Polyavino-Graph method. So it's important to be able to have such an L in the statement. So I'll give a long list of examples just so that it's clear that this comes up quite often. So in a paper of Fouvry-Vagnette on the divisor function in arithmetic progressions, there's a case with m equals 4, and the KIs are Klusterman sums in some fi of x, where fi are rational functions, which I won't write down. What else? So there's in a recent work with Fouvry, Ganguly, myself, and Michel, and in an extension by myself and Guillaume Ricotta, we have, again, M is arbitrary. Ki of x are Klusterman sums KLR of AIX, where R is 2 in the first paper and is arbitrary in the second paper. Which doesn't make too much difference, actually. And L is 1, so there's no extra factor, except, again, that we can expand. So what we did, the application of this, which I maybe mention later, if you insert, let's say, an additive character, you will be able to have a refined version in small intervals. So this is quite recent. Again, quite recent, Alastair Irving, in studying a divisor function in arithmetic progression, but with well-factorable moduli, needed something like this, with Ki of x is Klusterman sums, shifted Klusterman sums again, and L of x again is an additive character. And last example. So in a recent work of Blomer and Milicevic, they had a case where, if I remember right, M is 4, and it's again related to some Klusterman sums. Is that right, Georgie?
Yes.
Yes.
But you said the issue is solely the irreducibility.
Right. So this will be the, yeah. Okay, so this is to show that this comes up in many applications. This is certainly not an exhaustive list. And what we need to do is, or what I want to present is how one does handle such sums in many contexts. And this will be a well-motivated way to introduce one of the most important invariants of trace functions and of their underlying algebraic objects, the representation, which is the monodromy group. Okay, so what? Okay, so sometimes, so I'll start with a case where we can actually just deal with the Riemann hypothesis and basic formalism that we already know to handle such sums. So what we already know suffices to get cancellation in these sums. Oh yeah, maybe one example, I forgot while I was doing it. So this is a bit older, but there's this paper of Bombieri and Bourgain, which I mentioned once or twice, is also of this kind, with relatively complicated summands, which I won't write down. So, and here is the example. So, suppose you are interested in the sum in Irving, for instance, where the AIs are distinct. So, AI distinct, and I'm going to take L equal to 1. So, you have something like Klusterman sum in x plus A1 up to Klusterman sum in x plus AM. Okay, and that without having to do anything really, we can say that there is code cancellation. And what is important here is that the implied constant will depend only on that's in the applications. P is the main variable. P will go to infinity, but fixed. Okay, and the proof of this is not hard, and has to do with the ramification behavior.
Because I at least.
Yeah. So, and then the point will be that sometimes that's not the situation. So this is, as you'll see, quite easy from the Riemann hypothesis. It's if you expand it as a character sum, this will be a character sum in m plus 1 variables. By orthogonality, you'll probably kill one or two of them. So this is a character sum, additive character sum in about m variables. And if you translate this square root of p in terms of the character sum, this is code cancellation in character sums with arbitrarily large number of variables. So if you wrote this simply as a character sum, then it seems very hard. And if you shift a little bit the character sum randomly so that it doesn't refactor again in this nice way, you probably cannot do anything at the current time towards code cancellation. So the proof is not difficult. So you just isolate all the factors except one of them. So I guess, yeah. So I'll write k1 of x to be the product of the first m minus 1 terms. And k2 of x is the conjugate, but Klusterman sums are real valued, so I don't even have to write the conjugate, just do it for emphasis. And I'm going to apply the Riemann hypothesis. So KL2 is irreducible, so the sheaf doesn't change that. K2 is only geometrically reducible. K1 on the other hand is not. So usually, so this is a product of m minus 1 geometrically reducible objects, but they have rank larger than 1. In general, this product has no reason to be irreducible. So it turns out, as we'll see later, in this case it is, but at that point we don't know it. But even if we don't know it, we can at least factor it, decompose it into sums of geometrically reducible, take the product of all these, and we see that K1 is a sum of boundedly many, where the bound depends only on m, geometrically reducible, so technically there might not be geometrically reducible, but this is completely a simple issue to deal with. Summands, say mj. We can try and apply the Riemann hypothesis to every sum with mj times k2 conjugate. So when I claim that the sum of mj k2 conjugate is square root of p uniformly independently of j and p. So why is that? So we want to apply the Riemann hypothesis. So we have these assumptions here by this decomposition. The conductor of K2 we know is bounded by 1, or by a constant independently of P. And when I mention this decomposition of products, it is also such that every summand has conductor bounded by the conductor of the product of the things, which is itself controlled in terms of the conductor of the KL2s, which is uniformly bounded. So C of mj is bounded by 1, and C of k2 is bounded by 1. So of course here I'm also not taking care of the fact that the product might not be just absolutely a trace functions. You might have to take away the behavior of finitely many points and handle this separately, but that's not important. Okay? So the only issue is that can we have that mj is geometrically isomorphic to k2? That's the only thing that would prevent the Riemann hypothesis of this estimate, and it's not possible because k2 is ramified at minus am. So this is because KL2 is ramified at 0, and the formalism tells you that in this change of variable you need x plus am to be 0 for the ramification of k2 to appear, or 0 or infinity. So in fact k2 is ramified at 0 and infinity, but infinity does not help us because everything is ramified at infinity. Okay? So k2 is ramified at minus am, but I say that mj cannot be ramified at minus am. Let me do it here. So, but mj is a component of this product, which I called k1, each factor of which, each KL2 appearing in this, is unramified at minus am. That's because the AIs are distinct. So because okay? And it's part of the formalism, which is only easy to believe intuitively and not difficult to prove once you have the right definitions, that if you have something which is unramified, then any summand will also be unramified at this point. So mj is not ramified at minus am. And on the other hand, if they were geometrically isomorphic, then mj would have to be unramified at am. So contradiction. So it's very simple and extremely powerful, but sometimes it's not enough. So among the examples that I gave, which I think are all still here, right, the Burgess bound, you don't really need that, but because they are shift, the same argument works if the eyes are distinct. So some of these I erased. There was this example, which is not here anymore, where you had, so this would not work, for instance, for KLR of AIX, which is a situation in Fouvry, Michel, Riva, Sarkozy, for instance, and in FGKM and KR, where we really have this situation. In this case, everything is always ramified at 0 and infinity independently of I. So you cannot distinguish these sheaves just by saying that they are not ramified in the same place. So same ramification. Something just a little bit more complicated works for the Bourgain, or the Bombieri-Bourgain sum, actually. Okay, so moreover, so there's actually, even in that case that we began, there's sometimes this is not enough, because sometimes the AIs are not distinct. So when the AIs are not distinct, you cannot always expect cancellation. So it could be that the AIs come in pairs which are equal, and so you have a sum of squares. But in that case, you might want to know what is the alpha. So what is the leading term? You had something like alpha times p, where you want to know what is alpha. So if some AI are the same, especially, so in this special case, if m is even, and let's say a1 equals a2, am minus 1 equals am, so we have m over 2 equal pairs, then there's no cancellation to expect, but you might want to know what is the leading term, because sometimes that's what you need in application. And it turns out that the answer, trying to answer what is this leading term, trying to understand it, leads you naturally to this notion of monodromy group, which is a very important invariant attached to trace functions or to the underlying representations, really. So the answer will be that at least in some cases, and especially when you have, like, for instance, Klusterman sums, the answer, which is rather surprising and extremely useful applications, is that the leading term and the cases where there is a leading term is purely combinatorial, is independent of P or any fancy number theory. It is something which has to do only with some combinatorics, and this has very nice consequences. Okay, so this is related to what is known as the monodromy group, geometric monodromy group of the underlying representation. So I want to define this relatively quickly. So definition. So if you start with the representation ρ, so whatever that was, it was a homomorphism for a certain group pi1 which depends on P to some finite dimensional vector space. Then the monodromy group of ρ, so GG on ρ, is defined as the image. So you have this normal subgroup pi1G. And so what you can do when you have a group homomorphism, you can take the image. So this group, you should think of it as being rather complicated and difficult to understand in a really concrete way. It has many quotients which are quite delicate to understand, but if we have ρ, we have a way of seeing it as a subgroup of something a bit simpler. So we take the image. So this is an invariant of ρ, which is quite nice. However, it was realized at some point, I think by Grothendieck, that this is still too complicated because it inherits from pi1 of P a number of topological algebraic complexities which are more or less annihilated, at least made much more combinatorial and manageable when you take the Zariski closure. So what does it mean? So intuitively, this means that this geometric monodromy group is a subgroup of GLV, which you can think of as GLN of C, where n is the rank, given by algebraic equations. So like Philippe described in his lectures. So algebraic equation in terms of coordinates of the matrices and in terms of the determinant, and is the smallest such that cannot be distinguished from the image using just polynomial relations. That's a way of understanding Zariski closure. Cannot be distinguished. So typically it will not be the same at all. But if you're only allowed to use algebraic means, algebraic equations, things like bilinear forms and so on, you cannot distinguish the two, these two groups from the actual image of the geometric pi1 by polynomial equations. So by itself, this would not really probably be very helpful. However, we know something about that. So we know an abstract statement of the Lie, which as a consequence means that, in fact, this group, which sounds like just as complicated as maybe the collection of trace functions, because there's one for every trace function, can only vary in some discrete countable set, essentially, because of the rigidity of certain types of linear algebraic groups. In particular, it can be described by combinatorial data. And this has the effects of making a number of invariants of trace functions or of sums attached to them being purely combinatorial. So there's a very deep fact that the Lie proved on proving the Riemann hypothesis in the strong form that I mentioned, and which says the following. So G rho Giam is so up to a finite group, so up to a finite quotient. So it's built of out of a finite group, which is just the group of connected components, a semi-simple linear algebraic group. And what you should take from this, so even if you don't know really what is a semi-simple linear algebraic group, so in practice, especially in concrete cases, this means that this group is a product of some basic building blocks, which are the simple linear algebraic groups, of finitely many groups among the following. So a finite group, so it could be a finite group. This at first might seem like the situation that would be nice because it's finite, so we can understand them. In fact, this is a situation which is typically bad because groups are quite tricky objects, as I think the lectures of Harald have suggested. And then the other building blocks are big groups like SLV. If V has even dimension, it could be a symplectic group for alternating non-degenerate bilinear form on V. It could be an orthogonal group on V with respect to some periodic form or special orthogonal. And there's a bunch of others. A few exceptional groups, these things called G2, F4, E6, E7, E8. Okay. But essentially, once you've taken away the finite groups, you have a finite product up to maybe finite intersection. The product might not be completely exactly a direct product, but it's something that looks like a product of groups which are very well understood. And most of the time, they are classical groups, which we know from linear algebra. Okay? But for any given such nice linear algebraic group like SLV, there are literally uncounted many, I guess, subgroups of which it is a Zariski closure. So passing to the Zariski closure is really a highly simplifying fact. And it is an important feature of the theory that this simplification is actually not harmful for many applications. So there are some deeper applications where you actually cannot quite afford to take the Zariski closure, or at least if you do it, you then need to refer to deep results of strong approximation type in order to actually prove something. So applications to do with sieve in particular. But I don't want to talk about that.
You may just say that the semi-simplicity is proven by using a weak form of this, so weak error terms.
Yeah. Okay. Actually, I don't remember exactly how it's done. I think Katz has a different proof in his 4 lectures on Veil 2. Or is it the one you refer to?
No, I'm thinking of the Veil.
The Veil, yeah. Yeah, so I mean, this is one of the important steps on the way to proving the Riemann hypothesis. Okay, and again, so let me think again concretely. What can we say about this group? If you're given just the trace function, so if the trace function is purely abstract, it could be a complicated thing nevertheless to find it. So then you might want to just try and use this abstract structure theory of semi-simple groups to say something. But as you have seen in the applications I gave, usually for the sums of products, we don't have random trace functions. The KIs are usually taken from a list of trace functions that we already know, which are the ones that come up always in analytic number theory. And so it could be that someone has already computed the relevant monodromy group, and so you can use these results. As it turns out, this is the case. So Katz and a few other people, including Gaber, have computed or has computed, so also has computed this G rho Giam for many rows, so many trace functions, if you think in terms of trace functions. So including all those which have come up in analytic number theory up to now, as far as I know. So he once said that he doesn't write papers when he doesn't succeed. So it might be that sometimes people asked him and he didn't succeed. But so he has a number of books and articles and so on. So usually, if you come up with a reasonable trace function for analytic purposes, there's really a good chance that the statement computing this thing is found in the books of Katz. So for example, so the first big success in this direction was in the late 1980s for Klusterman sums. So for KLR, we have complete determination, and in fact, even of the Zariski closure of the image, the bigger pi1 completely. So you have either SLR when R is odd, or SP to R when R is even. So that's the situation. So these are nice because in some sense these are the nicest linear algebraic groups for many purposes. So in particular for KL2.
Why are these the nicest algebraic groups?
Well, I mean, orthogonal groups are a pain, as I'm sure you know. Well, I mean, they are not. I mean, finite orthogonal groups are really annoying. No, I mean, SP2R is really nice. Because typically when you get SP2R, the GREs is also the same. So for instance, that's and SLR is the one closest to just pure linear algebra, so I think. But I mean, you can disagree.
SP2R or SPR?
Yeah, R, of course. Yes, thank you. So there are rank R. So dimension of the analytic vector space is R, and it's either SL or SP. So something which is immediate from the definition and the formalism is that this is invariant under change of variable by fractional linear transformations. This changes the representation, but will not change the image up to isomorphism. So, which means that with the KLR of X, we get also the shifted ones and all the AI of X and so on. What other? No, I'm not going to give any other examples. I haven't written down any really concretely. So that's one thing, concretely. So nevertheless, you might think that, okay, maybe you come up with a function that Katz has never seen yet. You want to try and get a guess yourself. What does this thing look like? So as you'll see in application, it's good. The geometry monomy group is really complicated like SLR or SPR. So when it's simple and uncomplicated. So simple meaning that it's a product of just one single of these simple algebraic groups, and complicated in the sense that this algebraic group is not a finite group, for instance. So in that case, there's something quite wonderful which can suddenly help guessing whether you're in this type of situations, and this is the so-called Larsen alternative. So it's a theorem of Larsen, essentially, which has been generalized and studied by Katz a lot. Katz called it the Larsen alternative. So it's a concrete way to determine, if you're in one of these situations, up to some possible finite ambiguity by means which are similar to this Diophantine criterion for irreducibility. So that's rho representation associated to a trace function. So we need a small assumption which is not actually that difficult to either check or achieve by some twist, but I don't want to go too much into it. So we need to assume that if we take the Zariski closure of the whole group associated to this rho, we are not having a bigger group. So usually the worst that happens is that this Zariski closure is maybe this group times a finite central subgroup, and then by some kind of twist of determinant, you reduce to a twist of rho which satisfies this assumption. So this is true for Klusterman sums, for instance. Fine. I mean, it can be something delicate to prove, but it is often a situation to which you can reduce. So in that case, you have a way of saying a lot about the group with concrete means, which is a special case of Delin's equidistribution theorem. So I'm not going into Delin's equidistribution theorem here. But this is the key fact that is behind this and the Riemann hypothesis. So then, okay. So M4 of rho, the so-called force moment, be the integral over subgroup K of the trace of x to the power 4 with respect to our measure, where K inside the geometric Monodromy group, seen as a complex group, is a maximal compact subgroup. So for instance, if you know that the G geom is SLR, or if it is not the case, then this would be SUR. So you define this. Mu is the probability R measure. So this is some numerical invariant of the group. It really only depends on K, which is really only depending on the group. Then we have the following facts. So first, so these will be purely algebraic facts, and then I will translate this concretely for trace functions. So if M4 is equal to 2, so it's a number you have to compute it, suppose you can compute it, suppose you get 2. Then there are two cases. Either the group is finite, or it contains SLV. So this group I see as a subgroup of GLV. And if M4 is 2, so it's just a computation that you might be able to do, and then if you get that, then it could be finite, or it could contain SLV. So it could be a finite group times SLV. That can happen. But suddenly then it's big at least. So that's quite miraculous because a priori, this is about all the subgroups, essentially about all possible compact subgroups of a large linear group, and just computing some invariant of the R measure. If you get a 2, then you know that it's actually very, very restricted. And it is possible that it's finite. There are a few examples where this happens. And then you have to deal with something else in order to maybe exclude this possibility. So second case that I'm going to write, there are other cases, but I'll just write 2. Suppose the dimension is even. And suppose you know a priori, so this can also come just from the construction, the way one constructs trace functions or this representation, one might know that it has symplectic symmetry. That's something that can come from the data. And so that means you know for some reason that G geom is inside the symplectic group of V for some alternating form on V. Now you compute M4 again, and suppose you find 3 in this case. And so either this is finite, or it contains SPV. So this is really nice, but what does it mean in terms of the trace function? So because you might say this seems to require already knowing the group, or at least the K and knowing our measure and so on. So the second part is, so if you have a sequence Kp, so if rho p is a sequence of such things with a conductor bounded uniformly in terms of p and trace functions Kp, then so
But Emmanuel,
yeah.
are those absolute values around the trace to the x to the 4?
Let me check.
See, you'd be a bit worried about just say a central subgroup because it has a central character, which would make
I think it's, you're right. No, it's the absolute value for, yeah, because otherwise this would be often 0 anyway. Yeah, you're right, yeah, modulus of trace force power. Okay, let me not try and give a precise statement here. I'll just give a slightly more imprecise one, which is enough to guess what happens in many cases. So if the complexity of rho is small, and this can be quantified, then the point is that this M4 can be approximated, and again, this approximation can be quantified with the Riemann hypothesis as the average of the trace function to the power 4. So the force moment of the trace function of rho will typically be an integer, or very close to an integer, but quite an integer, and this integer will be essentially M4 of rho. So this gives you, if you're given a trace function that you can compute numerically, so this could happen if it's an exponential sum, for instance, and you're trying to guess, let's say, is the monodromy SL3? So somehow you know the rank is 3, or you might not know the rank, but you feel that this might be the case. You compute this for a suitably large p. If it's 2 point something very small, that really means that the M4 will be 2, and that the geometric monodromy group is either finite or contains SL3. And then there are tricks of cats to try and distinguish between the two. So usually in this case, you can say more. So there's a very famous example in the historical literature about that. So if you look at Klostermann's paper where he introduces Klostermann sums, so as you know, he proved that Klostermann sums are bounded by p to the 3/4 by computing the force moment, essentially. So what he proves?
1/4 is your normalization.
Yes, you're right. Thank you. Yeah, so with my normalization, the right bound is 2. So prove p to the 1/4. Proof by showing that the force moment is equivalent to 2, converges to 2 as p goes to infinity. Actually, there's an explicit polynomial expression where the leading term is 2 times p when you do the computation this way. 2 times p squared if you write the unnormalized Klostermann sums like he was doing. So in other words, implicitly, Klostermann was proving that for the Klostermann sum where the rank is 2, classical Klostermann sums, so either the monodromy group is finite or it contains SL2. So the right answer is that it contains SL2, which I think could also be done this way by computing the 6th moment. So you replace the 4 by 6, then there's a similar statement, and one can, I think, exclude the finite case this way. I mean, that's not how cats actually compute these monodromy groups. There are other techniques for this purpose, but so this shows that things can be done this way. So Daniel Wursch in a master thesis at ETH a few years ago computed the force moment for KL3. So he was able to basically reprove the monodromy of Klostermann sums in 2 variables as to be either finite or contain SL3 by this type of method. But it was a much more difficult computation. Okay, so now let's go back to sums of products. Only 5 minutes left. No, 15 because we started a bit late. Okay, good. So I need to go back. So why is that relevant? So why is this monodromy group relevant for sums of products? Well, one way of phrasing it, there are other ways, but one way of phrasing it is that if you know the geometric monodromy group as a concrete linear algebraic group, you might be able to say that your rho is geometrically reducible, even in cases where it's not obvious. So there's an easy fact, which is a special case of this property that the monodromy group and the representation cannot be distinguished from purely algebraic means. So rho is geometrically reducible, which is something we might want, if and only if, so when G acts on V, so the monodromy group acts on V as a subgroup of GLV, acts without invariance, non-zero, non-equal to V invariant subspaces. So it is irreducible as a representation of the vector space V subspaces. So if you know this group, then you might be able to say that, again, because linear algebraic groups have been studied for a long time, their irreducible representations are known, and typically, if you're given a linear algebraic group semi-simple as a subgroup of a GLV, you're able to say whether it's irreducible or not. Okay, so let's go back now to our situation. So now assume we have finitely many of these things, our representations, and we want to study the product. So the product of the trace function of the KIs is, so up to finitely many things, it's the trace function of the following representation. So we can write down precisely what representation it is. It's obtained as the composite of, so you start with the original one, you take the direct sum of the rho i's. So this will give you something in GLV1 cross VM. And then, so this implicitly maps some, so would associate the x to a vector, k1 of x, k2 of x, and so on. Now you want to take the product, and the product means you take the external tensor product of linear transformations there acting on the different factors. So this goes into GL, V1 tensor V2 tensor Vm. Okay, and here you have to think of G1 GM. So actually here I should say product, sorry. It's clearer if I write this way. So it's a product of linear groups. And if you take a tuple, then you send it to the tensor product of these things. And so if you know enough about the rho i's, you might be able to check that this composite is irreducible. So and so here we use another fact which is surprising. First time one learns it, at least surprising for me, is that so complicated non-abelian groups, especially simple but non-abelian groups, like those that Harald discussed in the finite case, but somehow there are analogies with this semi-simple case, tend to be very independent of each other. So complicated, so I'll just say non-abelian, it's a way of saying complicated. Simple linear algebraic groups. Tend to be independent of each other. So in the following sense, so this is a fact which I will state in a little bit unprecise way for lack of time and in a special case, but there's a general fact along this line which is known, at least called by Katz, the Gursa-Cauchy-Ribet criterion. And what it does is, in situations like the one above, it will tell you what is the geometric monodromy group of the first of the direct sum wise, given some facts, which could be non-obvious, but some facts on the row i's themselves. So, oops. So again, I'll do just the special linear case, but there are analogs for many other groups. So assume row 1 up to row m have that all their geometric monodromy group are special linear groups. So the VIs could be distinct, so the dimensions could be different. So assume also. So we want to say that then the monodromy group of the direct sum will be the product of the SLs. So this cannot be true if, let's say, row 1 is equal to row 2, because then the diagonal image is G, G, row 1 of G, row 1 of G, because they are the same. So assume there is no isomorphism of representations, so row I geometrically isomorphic to row J. So here you need to assume a little tiny bit more that I don't want to go into details. You might have to also show that rho I is not isomorphic to rho J tensor with a character, but let's not go into this. Usually that's what you need to check. Then, and this is the fact, the monodromy group, if VI, well, I mean, it's obvious if. So if the dimensions of the groups are distinct, then of course this will be true. But then you can compute the geometric monodromy group of the direct sum, and it is as big as it can be. So it has to be a subgroup of the product of the monodromy groups of the factors, and in fact it is everything. So this is a very surprising fact when one is used to abelian groups. So if you've taken an abelian group, if you take a product of abelian groups, there are usually many subgroups which surject on all factors. So this, basically, the content of this group theoretically is that a subgroup of this product which surjects to each factor and is not the graph of isomorphism between factors has to be everything. That's the group theoretic content, and it only is false for abelian groups. So there are many vector subspaces, so lines, let's say, in a vector space of dimension 2 which surject to both axes. In fact, that's the generic case. And this doesn't occur for complicated non-abelian groups. So I still have 10 minutes, yeah? Okay, so mark. So other cases exist. So this is not something that's related just to SLV. On the other hand, it is not true all the time. So sometimes, for instance, for orthogonal groups in either an odd or an even number of variables, I don't remember, this is false. So that's one way that orthogonal groups are bad. Actually, I was just saying one way that orthogonal groups are bad is that they don't satisfy always the Gursa-Cauchy-Ribet statement. Okay. So now let's go back to the applications. Actually, before I say this, let me state a corollary. So how do we use this corollary? So in the situation of this Gursa-Cauchy-Ribet criterion, the way I stated it, the direct sum is geometrically reducible. Okay? Because one can check that the product of the special linear groups acting on the direct sum of the subspaces is geometrically reducible. And that's not hard. So application. So let's consider now trace functions which are Klusterman sums with AIX P without assumptions on the AI. Why? I mean, if there's an invariant subspace, then it's not. I mean, then the external tensor product will be right. No, you're right. Yeah. Yeah. So the thing with trace function, the product. Yeah. This object. So it's because it's obtained. Sketch the argument. So we have this map here. We know what is the image. It's the product of the SL factors. And this VI is irreducible, and tensor reducible representations remain irreducible. That's an easy fact from representation theory. So no assumptions. Okay, so in that case, so as I said, it's not obvious because of the fact that the ramification is the same, but so one shows that the Gorsa-Kolchin-Ribet criterion applies to the distinct AIs. So meaning maybe some of these are different, and I put them together. At least that's the even case. In the odd case, one has to take into account possible dualities, which I don't want to discuss. Actually, I think I should have taken them into account. Yeah, sorry. So here, I need also to show that rho I cannot be the dual of rho j. So this would not be needed in the symplectic case. So this means that, concretely, this means in practice that Ki is not proportional to Kj, and Ki is not proportional to the conjugate of Kj. So I do the even case in any case to not have to distinguish between AI and minus AI. So suppose R is even, so 2, 4, 6, and so on, and then we are in the symplectic case, which I didn't state, but it works, and you can apply it to the distinct AIs. So hence, so if the AIs are all distinct, let's say to begin with, then the trace function, which is the product of these, is geometrically reducible. One knows its rank, it's R to the power m. And therefore, you can apply the Riemann hypothesis to compute many sums of products with these trace functions, including when the other factor L can be complicated. For instance, if L is not of dimension exactly R to the m, but is geometrically reducible, then without having to do anything, you get square cancellation. So you get something like, so KLR A1X. So this is again in the distinct case. So the implied constant will depend on the conductor of L and on the number of factors m, but that's all. For L geometrically reducible with, for instance, dimension of L distinct from R to the m. So for instance, if L is just an additive character with dimension 1, then this is automatic. So just to finish, yeah, I'm finishing extremely quickly. So if some AIs are not distinct, then one gets, so I don't have time to explain why, but it's not difficult from the same type of formalism, unless So in that case, unless kind of the obvious situation, so one gets cancellation, let's say for L equals 1. So in the paper, we explain more cases. So unless M is even, and the AIs come in pairs, come in M over 2 equal pairs. And in that case, so the leading term can be computed data of the monodromic groups is the multiplicity of the trivial representation in the tensor product of the standard representation of the VIs to the power, so multiplicity of AI, so distinct AIs. Okay. So in particular, it's easy to deduce that if the distinct pairs are distinct, so the M over 2 pairs correspond to M over 2 distinct AIs, which just repeat twice each, then this multiplicity will be 1. So this was the crucial point in the paper with Fouvry, Ganguly, and Michel, and then similar things for the paper with Rigotta, to show Gaussian distribution for divisor functions for intervals on average over the residue class. Okay, so I'll stop here. Thank you.
Are there questions or comments?
This theory, has it some intersection with Adelson-Sperber theory of exponentials, or do you think it's another world?
So the way I'm presenting it, it doesn't really have an intersection. In the sense that what they typically try and do is to work with higher dimensional character sums, and they want to find good criteria that ensure code cancellation.
Laurent polynomial, they're not...
Yeah, so here I'm not really doing, we're not really doing anything. We're trying to avoid multidimensional sums as much as possible based on the principle that this can be presented as a black box, and because it's a one variable sum, it gives code cancellation. And if you have two variable sums, then the only thing you can get for, if not for free but easily, is just you gain square root of p instead of gaining everything to get code cancellation. So of course there are situations where this will not be enough, but I think it really goes very, very far, especially in this type of applications in analytic number theory, where the sums that come up are often coming up in this form. In the circle method, that would not be the case. So when you do circle method to count points, then you naturally get Fourier transforms of characteristic functions of subvarieties. These are naturally high-dimensional objects.
I have the feeling that Adelson-Sperber theory has very, very few applications in our analytic number theory compared with what you said at the beginning of the talk.
So why is it clear that M4 rho is an integer?
Well, if you write it as an integral over R measure, then it's the integral of a factor over a compact group. So it's the multiplicity of the trivial representation is the corresponding. So it's not obvious if you just write let's say if you use a formula for R measure on SUN and write what it is, it looks like it's a complicated trigonometric integral that could be anything. In fact, it's an integer. It's actually a good check for computation. So if you do this M4 in a sampled way and you get like 2.35 something and the prime p is relatively large, that usually means there's a mistake in the program.
Okay, so if there is no more questions,
Thank you.